discuss. And now I will give the word to our coordinator, Silvia from Acciona.
Many thanks, Mirto. Good morning and welcome, everyone. Thank you so much for joining us and participating in this Master Project workshop. As Mirto mentioned, this project is focused on development of intelligent bulk materials for smart transport industries. The intention of this event is sharing the most interesting results obtained throughout Master Project. This project is funded with support from the European Union's Horizon 2020 research program. And I just want to say that we will be delighted to have your suggestion and question at the end of each presentation. And without any further delay, I would like to start with the event. I enjoy the workshop, and once more, many thanks for participating in this Master Project workshop. Thank you.
Thank you, Silvia. And also let me mention that the workshop is being recorded, and will be uploaded in our website. So if you are interested in going through it one more time, you can do so. I think we can start with the first session and the presentation of University of Salerno, which is entitled Design of Anti-De-icing Bulk Resins Based on the Joule Heating.
Okay, do you see me?
Yes.
And my presentation?
Yes, we can see.
Ok. Vai. Dove ti metto? Qui. Okay. Good morning, everyone. I'm Luigi Vertuccio, and I work at the University of Salerno with Prof. Liberata Guadagno. In this section, I will present a work about the design of the de-icing bulk resins based on the Joule heating. This work have been carried out in collaboration with Maria Dolores and the team of Apply Nano Solutions. My presentation will be discussed with the following outline: introduction, aim, experimental result, and conclusions. The epoxy resin are used especially in the field of aeronautical, mechanical, and naval engineering. Recently, these materials are exploited in the restoration, the structural adaptation of reinforced concrete elements when carbon fiber reinforced polymer are used. The last materials have been exploited in the civil engineering for realization of assembled structures such as a bridge, footbridges, offshore structures, etc. This work, the idea is to give the material a self-heating response, that is the icing function. The idea is to integrate the self-heating function in epoxy resin, making these materials applicable in the civil engineering for the production of bridges, terraces, roofs, that is, materials exposed to adverse weather conditions. Why? How? By introduction of carbon filler in order to obtain a conductive material which allows to have the Joule heating phenomenon when an external stimulus is applied, such as current, power, voltage. In my case, I used power. And these nanomaterials can be used for impregnation of glass fiber or carbon fiber reinforced polymer or as a coating. In this slide, I show the components of my materials used in the MASTRO project. The resin is the Gurit system, Gurit 180, where I have a precursor, an epoxy precursor, which presents two functional groups, two epoxy ring, and as hardener, I have an anhydride. As a fillers, we have the carbon nanotubes, two grade of expanded graphite. Particular carbon nanotubes are graphite strength 100, supplied by Arkema, and regarding the expanded graphite, we have ABG 1010 and ABG 1045. Supplied by Superior Graphite. In this work, the uniform dispersion has been obtained by ultrasonication for 20 minutes. And in this slide, I showed the 10 images of the different carbon fillers. So, in this work is very important the shape and the aspect ratio of the fillers, because this determines the electrical, rheological, and heating performance. Regarding the carbon nanotubes, we evaluated an aspect ratio of about 1000 obtained by datasheet of the carbon filler. Regarding the expanded graphites, we evaluated the lateral dimension and the thickness of graphitic blocks in order to evaluate the aspect ratio. Particular, in this case, we adopt a statistical approach where the system EXPG2 has higher lateral dimension, in particular between 29 and 91 micrometers, against EXPG1, for which I have a lateral dimension between 9 and 31 micrometers. The size distribution of the nanoparticles obtained by light scattering, dynamic light scattering, as you can see in the image B, are in agreement with the result obtained by the statistical approach carried out by scanning electron microscopy. In particular, for EXPG2, I have an average size of about 75 micrometers, whereas in the case EXPG1, I have 15 micrometers. For the thickness of a graphite block, we used the Scherrer law in order to evaluate the thickness of these blocks. And in particular, we obtained for EXPG1 a thickness of 32 nanometers, whereas for EXPG2, I obtained 27 nanometers. The ratio between length and the thickness allows to evaluate the aspect ratio. In particular, the system EXPG2, that is the filler ABG 1045, has a high aspect ratio between 1000 3.5 thousand against the EXPG1, which presents an aspect ratio between 300 and 1000. Another characterization was the X-ray photoelectron spectroscopy, XPS investigation, where with this measurement, we evaluated the amount of the oxygen on the nanofiller surface. And as you can see in the table, the system multi-wall carbon, the filler, carbon nanotubes EXPG2 have a lower amount of the oxygen. In this case, we can say that being most of the oxygen bonded over the edges, the system EXPG2 sample result less functionalized than the graphite EXPG1. Same thing for carbon nanotubes filler. So, electrical properties. In this slide, I showed the evolution, the behavior of electrical conductivity versus the amount of the fillers for all systems. The shape of curve is a typical shape, typical behavior, which follows the scaling law, and where the system based on carbon nanotubes has a lower electrical percolation threshold and higher electrical conductivity. In this case, the electrical percolation threshold is below 0.5%. Regarding the epoxy system based on expanded graphites, although we have a similar value in the electrical percolation threshold below 2%, this system differs for electrical conductivity value. That is 2-3 orders of magnitude. This difference is due to probably to the different interconnection between adjacent nanoparticles. In any case, when I have a high aspect ratio of the filler, I obtain high electrical conductivity. And in particular, if you see the system based on carbon nanotube and the system EXPG2, I obtained similar value in the electrical conductivity, 0.01 Siemens by meter, but for different amount of the fillers, 3 and 7% for system based on carbon nanotubes and system EXPG2, respectively. So, another characteristic is the viscosity. In this slide, I showed complex viscosity versus the frequency for all systems. And in particular, in this case, the epoxy resin has an eternal behavior. That is, in log scale, the viscosity is constant with the frequency. When I introduce the carbon filler, I have an increase of the viscosity and a change of behavior of the viscosity in shear thinning behavior. This change determines the rheological percolation threshold. So, in the case of carbon nanotubes, I have threshold is below 0.5, whereas in this case of expanded graphites, also in this case, I have a similar value below the 5%. The electrical conductivity behavior, we can see that I have a good correlation between the two percolation, rheologic and electrical, because in the value are very similar. Another characteristic regarding the expanded graphite and the low amount of the filler. In fact, as you can see in the MHB, low amount of the MHB, where I have the epoxy system based on ABG 1010, low amount of the filler determines a decrease of the viscosity. In this case, the graphite sheets with the lower aspect ratio acts as lubricant additive, whereas if you see the MHC, where I have the epoxy system based on ABG 1010, that is the system with a high aspect ratio, low amount of the filler determines an increase of the viscosity, always with an eternal behavior. So, regarding the electrical heating tests, if you see the electrical conductivity versus the filler concentration, in order to have a high flux of current, and that is high power applied, I need a high amount of the filler because I need a material with high electrical conductivity. that is in plateau condition of the behavior of electrical conductivity. For this reason, the most conductive samples have been chosen for electrical heating tests. In particular, in this work, we used 3% for carbon nanotubes and 7% for a system based on expanded graphites. The temperature has been evaluated placing a thermocouple in the center of the sample, as you can see in the image of experimental setup. Regarding the contact, I used the silver paint as a contact. And so, okay, the behavior, the test have been carried out at 3 different power, 3, 5, and 8 watts. And the behavior is the typical behavior of temperature versus the time. In particular, in the first stage, I have a linear trend to reach a steady state temperature, almost steady state temperature, because the range of time is liter, 20 minutes. But if you see the image D, when I apply the same power value, I have different voltage value. In particular, the voltage is lower for system based on carbon nanotubes and system EXPG2. That is the system with high aspect ratio. In this slide, I summarized the parameters, thermal and electrical parameters. And when I apply the low value of power, for instance, 3 and 5 watts, I achieved the same temperature value. In the case of 3 watts, I obtained 60 degrees, whereas in the case of 5 watts, I obtained 70, 75 degrees. But the voltage value are different. Whereas in the case I applied 8 watts, that is high value of the power, I obtained also a different value in the temperature. In any case, the best performance have been obtained with the system based on carbon nanotubes. Another characteristic, due to the shape and the aspect ratio of the fillers, is the distribution of temperature in the whole sample. In this slide, I show the thermal image, the evolution of the thermal image of the system based on carbon nanotubes, where the temperature is an average temperature in the black square line in the center of the sample. In the plateau condition, for this system, I obtain an uniform color tone, that is a good uniform distribution of the temperature. When I see the other system based on expanded graphite, I have a different situation. In fact, in this slide, I show the plateau condition, the thermal images of the system in plateau condition when I applied, in this case, a power of 2 watts for 20 minutes. And in this case, the system based on EXPG1, that is the image B, I have a strong disuniformity in color tone. In fact, on the left of the sample, I have a color, the color is red, that is a temperature of about 90 degrees, compared the blue in the center, for which I have 50, 55 degrees. Whereas in the case of system EXPG2, the temperature is more uniform than the system based on ABG 1010. Also in this case, the best distribution of temperature has been obtained with the system with the high aspect ratio, and in particular carbon nanotubes and EXPG2 system. And so, okay, conclusion. In this work, we developed a self-heating system with the de-icing function, and the morphological and the structural investigation highlighted that no relevant difference are detected in the structure of a crystalline phase. Wow, sorry. Do you see my screen?
Yes, yes, we can see.
Allora perché non va? Okay, sorry. Because if you see the X-ray, the exfoliation degree of the filler is different for a little amount. That is, the exfoliation degree of ABG 1010, I have an exfoliation degree of about 12. Whereas in the case system based on ABG, the filler ABG 1045 obtained an expression of 14. Where we have a little difference in exfoliation degree in the two fillers, the aspect ratio is very different because the lateral dimension of graffiti block is different. This difference in the aspect ratio and the shape determines a strong effects in the rheological, electrical, and heating performance. The electrical and the rheological data highlight a strong correlation between electrical percolation pressure and the rheological one, and we obtain similar value in the electrical conductivity for system based on carbon nanotubes, a system based on EXPG2, but with different amount of the filler, 3 and 7%. And finally, the best heating performance have been carried out for the system, for the 1D system, that is the carbon nanotubes, and the 2D system, where the 2D system has high aspect ratio. Sorry, I'm finished. Thank you for your attention.
Okay, thank you very much. I don't know if there are any questions. Okay,
I have a question, Luigi. Thank you for your interesting presentation. So, which kind of improvement you foresee for these materials with respect to Joule effect? So, in which way you think you can decrease the percentage of carbon nanotubes and graphite? So, which is the future?
The problem of amount of the graphite is in this case the viscosity of the application, because for instance if the idea is the application sector in my idea, because I can use the three systems are very similar in performance. The problem is my generator on aircraft and a car is limited or not. I can use high voltage, for instance, I can use high value of current. In my opinion, this system I can use this system for heating, self-heating and de-icing function at land, for instance, at home, in the production of, for instance, roofs with the de-icing function. When I use carbon fiber, for instance, no, glass fiber reinforced polymer. In this case, I can use the voltage, value of voltage at home. For instance, at home, I have a voltage of about 220 20 volts. To reduce these electrical parameters, I can increase the amount of the fillers, but in this epoxy resin is very difficult because if you see, for instance, the rheological properties, in the rheological properties, we have a strong increase of viscosity. And this has a problem in the process of, for instance, liquid infusion of a carbon panel or a glass fiber panel. A different approach, in my idea, in order to have an external stimulus with low value, for instance, low voltage, is to use an heating element, because during the MASTRO project we used another approach based on film meter, where we used always the filler ABG 1010 and ABG 1045. Anzi, I have I have a time? C'è un po' di tempo?
Yes, yes.
Sì, ok. For instance, vediamo condividi. Ho tempo. Allora, condividi. Ok. For instance, ok. Do you see my presentation? Okay.
Yes.
Okay. For instance, in order to have a low value of the voltage, for instance, we can use an film meter, also as I show in this slide, where we use the ABG 1010 and ABG 1045 with a polymer PVA. In this case, as you can see in the table, I have the same different electrical conductivity for different aspect ratio. In the case of epoxy resin, I obtain a maximum value of electrical conductivity of about 0.01 Siemens by meter. Whereas in the case of in the case of a film meter, for instance, I obtained 3000 Siemens by meter. This allows to apply an external stimulant soft. For instance, in this case, in order to have an increase of temperature of about 30 degrees, I used 60 volts for system ABG 1045. Whereas for similar temperature, in the case of epoxy system, I need 200, 300 volts. For this reason, in my idea, in order to have low external stimulus in current, power, or voltage, we have to change the approach. Epoxy resin when I have an high power, and a film meter when I have I have a low power value. Okay, because the viscosity is a problem for a production of carbon fiber panel. This is a limit of these systems in the process. Sorry, Giuseppe, I don't the microphone. Giuseppe, microphone. Non si sente.
Don't worry. Don't worry, Luigi. I sent you a message.
Yes, I'm sorry, Luigi. I had a problem with the microphone. Now it seems it's okay.
Ah, okay.
Thank you for the explanation. But I heard you, so it's okay. Thank you very much. Very nice talk.
Okay, are there any other questions for Luigi? If not, I think we can move forward with our next speaker, who is Andrea Tinti from CETMA.
Can you hear me?
Yes?
Okay, I'm sharing my desktop. Can you see my desktop?
Yes.
Okay. Good morning, everyone. My name is Andrea Tinti, and I'm a technical person in charge for a master project on behalf of CETMA, Italy. CETMA is a private, non-profit research and technology organization that carries out applied research and supports the innovation process of industrial enterprises, mainly by offering to its customers consultant activities. CETMA employs about 65 people, about 30 of them being part of the Advanced Material and Process Department, where CETMA has participated in master project. The main strength point of CETMA is the availability of integrated skills in polymers and composites field, from design, testing, and simulation of both materials and components to setting up of the related manufacturing processes. In the framework of Master Project, CETMA has led the work dealing with the design and development of the smart thermoplastic materials at component level, and now I'm going to present a review of main results obtained. 4 use cases are considered, addressing 2 out of 3 application sectors, automotive and aeronautics, and 2 out of 5 self-responsive functionalities, self-de-icing and self-protection from electrostatic discharge. In this table, a few other technical information are reported for each case study, such as the matrix material, the carbon nanomaterial, and the production process. Most of technologies are to be demonstrated at the prototype level in a relevant environment, that is TRL 6. So, okay. Below is reported a glossary about the required self-responsive functionalities to be achieved by incorporating electrical conductive nanomaterials into the base matrix. In particular, multi-wall carbon nanotubes were used in the form of compatible master batches provided by the project partner Arkema. These functionalities are self-de-icing based on Joule effect heating, that is to avoid ice formation due to cold weather, and self-protection from electrostatic discharge, that is to avoid static charging to build up to a level which may create a spark. With respect to a typical percolation curve of an insulating matrix loaded with a conductive filler, these functionalities are placed at the limits of percolation range. Static protection needs a lower electrical conductivity and then a lower carbon nanotube content below the percolation threshold. On the other hand, Joule effect heating needs a higher electrical conductivity and so a higher nanotube content above percolation threshold. So, as the input data for the smart materials development, first the general smart requirements were defined for each of the materials of interest by defining proper key performance indicator and corresponding verification criteria. Then the specific thermoplastic matrices were selected by choosing proper grades of proper commercial grades of knit polymers. And also preliminary compatibility and dispersion tests were performed between the addressed matrices and the carbon nanomaterial that, as reported, were Arkema's carbon nanotube master batches. So the work done can be briefly summarized as reported in this slide. Thermoplastic nanocomposites and related manufacturing processes were first developed on laboratory scale, that is at specimen level. Self-responsivity was measured, and also the other general requirements set for each case study were checked. With regards to case studies based on Joule effect, predictive models were internally developed and used for the purpose of preliminary component design. For each of the addressed matrices, a number of nanocomposites with varying carbon nanotube content have been produced by means of thermoplastic melt process technologies, mainly single and twin screw extrusion. The optimal compounding parameters were defined to obtain a uniform filler distribution that is essential to build a conductive network within an insulating matrix at lower concentration. Transmission electron microscopy was used as a direct mean to evaluate the homogeneity of carbon nanotube dispersion. Then a complete characterization campaign of the nanocomposites was performed in order to analyze the influence of the carbon nanomaterial content on the properties of the loading material. First, electrical conductivity was measured in order to determine the percolation curve and the conductivity plateau. Theoretical percolation equation was used to fit experimental data in order to find all parameters of statistical percolation model, especially percolation thresholds. Rheological tests were performed to evaluate the increase in melt viscosity upon addition of nanotubes, this affecting material processing in both the compounding step and also the subsequent forming step for the manufacturing of the intended demonstrators. Finally, mechanical analysis has been carried out by means of tensile test to evaluate material embrittlement upon high loading of nanofiller, resulting in reduced material performance as constant strain of break. This slide summarizes in a very concise manner the technical approach used for the smart thermoplastic development. Now let us comment a few details more about the subsequent task of self-responsivity measurement and preliminary scaling up activities. The only aeronautic case study between thermoplastic ones, of course, was a component of an aircraft fuel system with self-protection functionality from electrostatic discharge. After complete development and characterization of the matrix material that is polyphenylene sulfide loaded with carbon nanotubes, the work has been focused on the whole component material. In fact, this case study is a continuous carbon fiber reinforced composite. The proposed manufacturing approach was the production of an organosheet by film stacking process to be formed in the desired shape by means of compression molding. This technology was proposed, followed by induction welding as a possible solution for manufacturing of hollow shapes. With regards to the reinforcement, a proper commercial carbon fiber fabric was used. A preheat treatment was studied to remove the epoxy sizing agent coating from carbon fiber before the impregnation process with thermoplastic matrix. Regarding the PPS matrix, it was found that the percentage of nanotubes should be set at about 2% by weight to get the overall conductivity to mid static discharge level. Then the film staking process consisted of overlapping on each other a number of plies of both dry fabric and thin polymer film with the proper fiber matrix weight ratio, and then compression molding the sandwich to obtain a flat laminate. Impregnation effectiveness has been evaluated by means of void content measurement. A mean value of less than 3% was obtained, that is close to aeronautic standards. Mechanical performance were evaluated by measuring both the tensile properties and interlaminar shear strength that is closely related to the fiber matrix adhesion properties. In respect of a typical thermoset carbon fiber composite, obtained results are influenced by the lack of a specific thermoplastic sizing, which would result in a strong chemical bonding between carbon fiber and PPS matrix. To get the best mechanical performance of the component, an alternative carbon fiber with the specific thermoplastic sizing could be used in a future development. Finally, self-protection effectiveness has been checked on the molded organosheet by measuring both surface and volume resistivities, showing that the anti-static requirements were widely fulfilled. In the last part of the work, the moldability and weldability of the organosheet were preliminarily evaluated, showing good results in terms of both surface finishing and overall quality of the welded joint. A few details more about this case study will be presented later on during the workshop within the third session that is dedicated to the final demonstrators. Okay, let us move on the automotive case studies with self-de-icing functionality. We have the door gasket, the windshield coil cover, and the pipeline component of an electric vehicle's battery filling system, this one. After complete development and characterization of the materials of interest that are thermoplastic vulcanizate for the door gasket, ABS for the windshield coil cover, and thermoplastic polyurethane for the battery filling system pipeline, the work has been focused on self-responsiveness measurements. Self-de-icing tests were firstly performed on a sheet specimen. A nanotube content was used such that electrical conductivity was in the order of tens of Siemens over meter. All material resulted in useful de-icing time of less than 30 minutes to melt a 5 millimeter thick ice slab frozen on the material surface at low applied voltage between 12 and 24 volt DC and minus 25 degrees external temperature. In most cases, the maximum allowed surface temperature, that is about 60 degrees, was significantly exceeded. This requirement was set for safety reasons, considering the possibility that the component come into contact with human skin. In such a case, within electronic control design activities, a discontinuous on-off operation mode has been set for the smart components to work properly. This approach is to be preferred with respect to use a lower applied voltage because at the maximum available electrical power, the heating rate is as high as possible, and then the de-icing time is as low as possible. Then a simplified analytical model of Joule effect was developed, arising from an energy balance of the system under study. The analytical model was validated by comparison with available experimental data, and then it could be used to predict self-de-icing behavior of the materials of interest in any size, geometry, and operating condition. That is for the purpose of component design. Okay, after preliminary consideration on simple sheet shape specimens, further tests and calculations were performed with regards to each case study in order to take into account the specific geometries, production processes, and component requirements. Starting from the windshield cold cover, it has been proposed that the smart functionality can be limited to a thin surface layer in order to save the expensive conductive material and also preserve component mechanics. In fact, it was found that strain upbreak of ABS nanocomposites continuously decreases with the nanotube content, indicating a significant embrittlement of the polymer matrix upon addition of the conductive nanofiller. Also, in the final configuration of the component, the heating layer that is under voltage will not be in direct contact with the snow or the ice, because this is partly conductive and can cause short circuits. Between these layers, there will be a neat ABS layer. So the heat has to go through this insulating material to reach the outside environment. To check if this layout does work, a numerical approach has been used. So parametric simulations have been carried out to find the relation between the electrode distance and the applied voltage to get a maximum surface temperature of the ABS sheet here at steady state of about 60 degrees. That is the required safety limit. The distance between linear electrodes has been ranged from 5 to 20 centimeter, and the voltage range from 24 to 48 volt DC that are commonly available in work vehicles and sport car. So the numerical approach consisted of the following steps. First, a parametric study was done to obtain temperature versus distance and voltage curves. Then, to seek couples of voltage and distance values for which the temperature is equals 60 degrees. And finally, to reconstruct distance versus voltage curve for the target temperature. As shown, a linear relation between distance and voltage was obtained, so the needed distance can be calculated given an applied voltage and vice versa. In all cases, the five combination of voltage and distance, the numerical model predicted a useful de-icing time of about 20-25 minutes to melt a 5mm thick ice slab frozen on the material surface at -30 degrees external temperature. So the proposed layout was found to be effective. Again, a few details more about this case study in the final configuration will be presented later on within the third session of the workshop. Moving on, the battery filling system pipeline. The main characteristics required to the standard component are flexibility, transparency, and electrical insulating surface. Two possible solutions have been proposed for the smart pipeline. Option A is a one material pipeline fully made of thermoplastic polyurethane loaded with the nanotubes, so completely black and having a conductive surface. On the other hand, the requirement of flexibility would be satisfied. In fact, it was found that strain of break of thermoplastic polyurethane and nanocomposites at high loading of nanotubes is quite unaffected in respect of the NIT metrics. The one material pipeline would ensure the availability of a real scale prototype to validate the constituent material for self-de-icing functionality only. Option B, on the other hand, is a co-extruded pipeline that is an insulating transparent shell made of TPU and a conductive black core made of TPU loaded with nanotubes. The black core is rod-shaped, permitting this way the inspection of the liquid in the pipeline, so to make noticeable if any gas bubble form inside the water circuit. So in such case, all requirements would be fulfilled. Moreover, because this component was also required to be dissipative, the TPU transparent shell has been compounded with an inherently dissipative polymer, IDP. No carbon nanomaterial was used to increase conductivity for static protection because, as reported, the incorporation of carbon nanomaterial in a clear polymer matrix makes it completely black, also at very low loading level. Proper commercial IDP master batches suitable for TPU matrix were selected and tested, resulting in anti-static surface with measured resistivities useful for electrostatic discharge. Then a number of production trials of the smart pipeline were performed by means of continuous extrusion process for both option A and option B, resulting in good quality, flexible tube specimens. In the second case, because co-extrusion technology was not available at the laboratory scale, an assembled pipeline was produced for the sake of component testing, made of nanotube loaded wire properly fastened onto a NIT matrix tube. Both the one material pipeline and assembled pipeline were tested in self-de-icing after filling the whole tube cavity with water and freezing to form ice. Useful de-icing time of a few minutes were measured to melt the ice inside the tube at low applied voltage, 24 volt in the first case, 29 in the second, and about minus 10 degrees external temperature. Also, the maximum surface temperature reached during the test time always stayed below the safety limit fixed in 60 degrees. The developed analytical model of Joule effect was properly modified to take into account the specific characteristics of this case study, that are the tube-like shape of the specimen and the boundary condition of the self-de-icing test. It should be noted that the simplified model only considers ice-sensible heat, neglecting its latent heat of fusion, and as a consequence, transient phenomena like phase change at constant 0 degrees temperature, and then the de-icing time cannot be predicted. But on the other hand, the model describes the heating behavior of the system tube plus ice in a freezing environment until a stationary temperature state is reached. Anyway, also in this case, self-de-icing functionality at component level has been demonstrated. Finally, regarding the door gasket case study, a few design simplifications were preliminarily introduced before performing a number of production trials of the component by means of continuous extrusion process. The extruded gasket loaded with nanotube in respect to the knit one made of thermoplastic vulcanizate exhibit higher rigidity with a tendency to break, thus not complying the requirement of flexibility and deformability. Then a self-heating test at room temperature and 9 volt applied voltage was conducted on a specimen of the produced gasket loaded with nanotubes, resulting in an inhomogeneous heating profile with highest temperature close to the measuring electrodes. On the other hand, the material far away remained quite cold. This behavior is also undesired for an effective self-de-icing device. So, despite the achievement of self-de-icing functionality at material level, as a consequence of a high electrical conductivity, the observed material brittleness and poor thermal conductivity are not suited for a component with sealing properties and fast and uniform heating response. Probably in this case, the master approach is not appropriate, and an alternative solution would be, for example, to leave the heating function to the inner metal core that usually is drawn within the rubber gasket for interlocking to the door frame of the car. Okay, so to draw main conclusions, at the end of the work, in almost all cases, when available the proper technology and equipment, developed material and process recipes were transferred at component level in order to validate formulations and parameters in real size and geometry. Regarding the only aeronautic case study with self-protection functionality, the hardest challenge was about the manufacturing process rather than self-responsivity, because in this case, a relatively simple anti-static surface was required, needing a low nanotube content. In fact, an electrical conductivity suitable for static protection was obtained at 2% weight nanotubes. Also, a multi-step procedure has been proposed and demonstrated as a possible solution for manufacturing of hollow shapes, where both the compression molding and induction welding are of great interest in thermoplastic composites manufacturing for aeronautics. And finally, as reported, the proposed organosheet was produced with the low body content and pressed into semi-complex shapes. Regarding the 3 automatic case studies with self-de-icing functionality, in this case, the main technical challenge was to demonstrate an efficient Joule effect heating, because this requires a high nanotube content above calculation threshold. A suitable electrical conductivity was obtained, always in the order of tens of Siemens over meter, thus effective for a self-de-icing behavior at low input voltages, below 24 volt DC, and so safe for users. All materials, when tested in the form of a sheet specimen, resulted in useful de-icing times of less than 30 minutes to melt a 5 millimeter thick ice slab frozen on the material surface at minus 25 degrees external temperature. And finally, a simplified analytical model of Joule effect has been internally developed and validated for the purpose of preliminary component design. And that's all from my side. Here I reported all details to get in contact with Chetmar for any reason. Thanks very much for your attention and available for any question.
Thank you, Andrea. Are there any questions for this presentation? Okay, I don't think so. I think we can move to the next session, which is about the smart functionalities models developed by IPC with the support of University of Salerno.
Okay, I will share my screen. Hello, everybody. Oh, excuse me, I make a mistake. Okay. So, hello everybody, it's Patrick Devailly from IPC. So IPC is a center dedicated to research, research center dedicated to composite material and thermoplastic, where I will discuss about, I will show what we do for the smart functionality model and what the strategy of modelization for all MASTRO project. So the objective was to define a best modeling strategy to take account all phenomena and to validate new models with partners and compare to macroscopic tests. And we also discussed about user applications that we developed. The problem for this modelization of MASTRO was the size of the parts. Why? Because if you take a part like a plane, we have different scales, and you see we go to the nanometer from nanometer to meter, and it is impossible today with standard software of simulation to integrate directly in direct numerical simulation. So we have to use a multi-scale homogenization. So we will show you the approach with 3 parts for the nanoscale modeling. After I show what we do at the microscale modeling, and after we finish with the macroscale modeling and the modelization of demonstrator. So to begin, we will discuss about nanoscale modeling with this part. So the strategy for the homogenization is to take at the nanoscale model to take account the the effect of matrix on carbon nanotubes, and to integrate in an application and to have a modelization of electrical conductivity, thermal conductivity, and mechanical conductivity. And after, we homogenize and we grows up for the scale. So to begin with the nano scale, we will discuss about RV, which is a box, and in this box we make three methodologies. The first is the molecular dynamics that Greta will present of Greta from UNISA, and after I will show you the both with finite element method and the analytical method. So Greta, if you want to take the end.
Yes.
So you take me when I can pass a slide, no problem.
Yes, can you hear me?
Yes, no problem.
Okay. So I think, am I sharing my screen? Do you see my screen?
Yes.
Okay. So all right. So yes. Let's see. All right. So good morning, everyone. And I am Greta Donati from, I worked on a MASTRO project at University of Salerno during my postdoc in Professor Giuseppe Milano research group. So as Patrick was saying before, this multi-scale approach was absolutely important to try to understand and try to give a better insight in the main molecular phenomena taking place in these composite materials. So first of all, we gave an insight and we modeled explicitly both the carbon nanotubes and the polymer matrix. In this way, we could simulate the system morphology and understand how this morphology can impact both the electrical and the thermal properties. And we did this by a molecular dynamics simulation by using the Occam software developed in Professor Milano research group. Then we move to the simulation of electrical conductivity and so the piezoresistivity by explicitly evaluating the effect on the electrical conductivity of an applied strain that could be both an elongation or a compression. And we did this by both using the Occam software for simulating this system and then with post-processing in-house developed code. Regarding the thermal properties, we evaluated the Joule effect of these different simulated morphologies, and we explicitly understand and evaluate the thermal properties inside these systems. We also deeply investigate which are the main factors influencing the Joule effect properties, in particular the voltage, the concentration, the aspect ratio, and so we could in this way try to also help our colleagues to better also design new materials. So first of all, we give a brief introduction to the Joule effect. What did we do? As we said before, why do we need to simulate morphology explicitly of carbon nanotubes? Because we know that carbon nanotubes assemble at nanoscale. So it's important to actually try to simulate and evaluate how these different morphology can impact the electrical properties. So we simulate all these different conditions, and for each one we evaluate the electrical properties. How did we do this? So we do this by using the percolation law, because we already know from literature and other studies that the percolation law is able to properly describe the behavior of this system, that at the beginning they are not conductive, when we just have the polymer matrix, but then we increasingly adding carbon nanotubes and increasing their concentration, we have an increase of conductivity that can be well described by this law. So we evaluate and we simulate the different percolation curves for the different morphologies. At this point, what did we do? The electrical conductivity was calculated at nanoscale level, and also the temperature, that is of course dependent on the local concentration of carbon nanotubes, was evaluated by explicitly solving the heat diffusion equation, as we can see here. So here we have local electrical conductivity evaluated on the different morphologies, and also for all the different concentrations we simulated, and then we solve the heat diffusion equation by including the term coming from the Joule effect, so to the fact that carbon nanotubes are conductive, and then we could evaluate the local temperature, the local different temperature. As we can see here, we can have a correspondence between the local density of carbon nanotubes and the local temperature. So these pictures are saying us that we are properly simulating where temperature is higher, because in those regions the carbon nanotube concentration is higher. So after we evaluate the local temperature, we let this this local heat diffuse. And what did we gain? First, as we said before, we evaluate the Joule effect at different carbon nanotube concentration, as we can see here, and of course we obtain different curves of the heating rate as a function of the applied voltage. In this way, we can both evaluate the concentration, carbon nanotubes concentration effect, and also the voltage effect. So as we can see here, in this case, this is for the random morphologies, and in this case, our percolation threshold, so the concentration after which we can say that our system is conductive, was around 3% of carbon nanotubes concentration. So what do we see here? That at low carbon nanotube concentration, even if we apply high voltages, we do not have an important gain in the heating rate. But of course, if we increase the carbon nanotube concentration, this effect is of course higher. So we have an important increase at higher voltages. However, if we, for example, this picture is also saying us another thing, that if on the other side, we need to, for our possible application, technological application, we cannot reach higher voltages because there are limits about that. For example, we say we are around 40 voltages. We have to say here in this area, we can say that we do not see an important difference. Also, if we increase the carbon nanotubes concentration. So what is this graphic saying us? It's saying that if we need to say at low voltages, even if we use lower carbon nanotube concentration, we do not have a very different behavior. So if, for example, having a system much with a higher carbon nanotube concentration can be or expensive or can change drastically the performance, the characteristic of the material. So if we have these limits, we are sure that, for example, around 40 voltage, we can stay also at a lower carbon nanotube concentration, with having effects similar to the one we could have if we increase the carbon nanotube concentration. So this indication can be useful for practical application, because sometimes we can have limits in the voltage, applied voltage, or in the concentration. So however, beside this indication that can be general in terms of behavior, general indication, we also perform comparison, direct comparison with experimental results. Of course, adapting our nanoscale approach to the macroscopic one. Here we evaluate our simulated three different morphologies. So here we are adding another variable to our knowledge. So beside the voltage effect, also the morphology effect, and compare our result with experimental one. Here we use three different experiments taken from literature, where the experiments were performed by using thermoplastic matrices. And what is this graphic saying us? So that actually the experimental results lie more or less exactly in between our random and our assembled morphologies, both in liquid monomer or in linear polymer. So in this case, we can say that in thermoplastic matrices, our model are at the boundaries. So the actual experimental morphology could be in between both of them. Although, for example, we see that in this experiment we have the results much closer to the assembled morphology, so to a situation that is closer to this one. However, we can say that the agreement in terms of range of interests, there is a good agreement. So we can say that we can actually explicitly consider the evaluation and the comparison with the experiment. And so also that our model is, can actually work properly with this in comparison with the experiments. Of course, our results lie in between because, of course, we are talking, so the experimental one lies in between because of course, we are modeling a specific like morphologies that of course are not exactly equal to the experimental one that probably lies in between. However, if we compare our results, simulated results, with the experiments in epoxy resin matrices, we can see that our results are similar to the experimental one in terms of random morphology. So in this case, we can say that in epoxy resin matrices, the morphologies taken by carbon nanotubes can resemble more a random one instead of an assembled one. Another effect we taken into account was the effect of the heat diffusion coefficient that influences the homogeneity of the diffusion. We know that higher is the heat diffusion coefficient, more homogeneous and in a faster way will be the heat diffusion. And so here we can see at the beginning of our simulation, we have, of course, here local higher temperature due to the carbon nanotubes. After like it was after our simulation, we can see that with a lower heat diffusion coefficient, we still can see areas, regions in which temperature is locally higher and other in which it's colder. While with higher heat diffusion coefficient, we already have an homogenized temperature. So also in experimental results, in experiments, it's important also to take into account this effect, because of course, if we want to reach immediately in a small amount of time a homogeneous temperature, we have to take into account the effect of the diffusion coefficient. We also work on piezoresistivity. And we also model this one. How? Also in this way, we take into account the different morphologies and of course the effect of different concentration and evaluate the effect when applying a strain, an elongation or compression. So we started from our system, unperturbed system, and then we applied both elongation or compression. We did simulation in this case, and we evaluate the gauge factor. So what do we see here? We have the simulated gauge factor as a function of the strain, so zero strain, elongation or compression in the same amount, and also evaluated at different concentration. As we said before, the random morphology percolation threshold is around 3, and what we see here is a very different behavior close to the percolation threshold and at higher concentration. This trend is in agreement with the experiment because we know that higher sensitivity for piezoresistivity is observed close to the percolation threshold. And also, if we compare our results also in terms of delta R over R0, we can see a very similar behavior with like the experimental one. And also, given a specific concentration for like 3%, we can see a different behavior for elongation and compression that is also observed in experiment, where the elongation gives, when piezoresistive in terms of elongation is higher compared to compression one. So in conclusion, regarding this nanoscale part, we will say that first of all, it was very important to give this insight also for to coordinate ourselves with our colleagues for the microscale and macroscale models and simulation. It was very important to actually give an insight and understand at the microscopic nanoscale level the effect of morphology of concentration, because this simulation and our results that we observed being in agreement with also with the experimental one could help in understanding the reason of the limits of existing materials and also to try to improve them. So like at this point, I think like for nanoscale part, I am done and I give back the work to Patrick. Thank you very much.
Thank you, Rita. So I will reshare my screen. So to continue what Rita showed you, we will continue with the nanoscale approach, but with the finite element method. So we use the same RVE. We generate the structure of the material. We generate a mesh with finite element method. We simulate the electric field or thermal field or mechanical field, and we obtain the evolution of the conductivity tensor for electrical phenomena or mechanical tensor or thermal tensor. So what it is very important in this generation, it is to take account the aspect ratio, the orientation of nanotubes. We can generate many cases of what we want. Here we can see an example with the generation of different volume ratio of carbon nanotubes. And when we do this, we make a meshing. On this mesh, we use a voxel approach, which is which require less elements than the tetrahedral mesh, but it is less precise. So the calculation is longer if we use a tetrahedral mesh. If we use it, we obtain the homogenization, like you can see, and we can see in some case some percolation, and we see the evolution of electrical tensor versus carbon nanotube concentration. The big problem of this approach was the generation of what we call tunneling effect, because with the finite element method, unlike that Greta showed you, we cannot see after a mechanical compression or mechanical traction on the RVE, we cannot make an evolution of this tunneling effect. So it is very a problem with this approach. So it is why we develop an analytical approach, which is a web application, to determine quickly this carbon nanotube value, and we develop in Python, and we integrate it in a web application. So you can see the address, and it's very useful, friendly to use, and to obtain the curve. Now we'll switch to the microscale approach. So we obtain from the three methods, thermal, mechanical, and electrical matrix, tensor, to go to the microscale level. So we integrate with graphite or continuous fiber or discontinuous fiber, and we will make the same scenarios at nanoscale to obtain the value at the microscale level. So here you can see the two phenomena that we want to modelize. The first is the piezoresistive effect. So we take the RV and we apply a compression or traction effect on the RV. So you see that the current density field is not the same. We have an evolution. So we can directly calculate the Gauge factor. And for the Joule effect, we make the same thing. We apply thermal field, we apply an electrical field, and we obtain the thermal field in the RV, and we obtain the thermal conductivity tensor. So after, when we do this, we go directly to the macro scale simulation. So the idea is the last to make the multi-physical simulation at this scale. So to do this, we employ also the Joule effect and piezoresistive effect. So we make some comparison on the specimen to validate this model, and after we deploy them on the demonstrator of MASTRO project partners. So today it is a publication of Tunisia. They put an electrical potential of a little plate, and we see the evolution. It is the same case that Rita showed us before. So we have a good evolution. Another example which do by Setma, we use a plate with different kind of thermoplastic, with different content volume of carbon nanotubes, and we apply electrical potential, and we will see with a variation of electrical potential during the simulation if we keep the same evolution that the experimental test. So you can see we have the same evolution for each materials. So it's very good thing. So we validate the Joule effect model. Regarding the piezoresistive effect, we take an experimental test of UNISA with evolution of an alternative force in the specimen. We make an alternative traction and compression effect. So we use an elastoplastic model in simulation, and we integrate them at the same level that the experimental data. We position a specific sensor to obtain the electrical field and the current density field. If we do this, you can see at the upper we have the simulation, at the under you have the measurement. Sorry, but don't take count the scale at the right in red, because we have not, it is a good value, but we have not the same scale. So it's I make this a mistake at this, but it is the good value. So what we can see, which is very important, it's the residual resistivity that we obtain in the plastic model, and we see we have the same phenomena in the experimental data on the simulation. To finish, we integrate the phenomena of auto-curing. So in this case, we have to integrate three phenomena: the thermal modeling, the electrical modeling, and the curing modeling. So we couple all systems, and we do this on a specific on a little plate, and we use an evolution and capture rate the curing law of a specific epoxy resin, excuse me. And we can see here, if you make an electrical potential in this plate, we see that we have an increase of temperature. Due to the increase of temperature, we have also an increase of the degree of cure. And do the evolution of the degree of cure and the temperature with the thermal expansion of the taking account the shrinkage of the resin, we can see how the stress and the strain of in the plane during the process evaluate. And it is to capture the residual stress, what we call the distortion after the process. So we can do this, and you can see here, if we increase the voltage, we have quickest curing. So we'll see it's a good thing. So now to finish, we go to the macroscale simulation of demonstrator. So in the MASTRO project, we use two demonstrators. One of them is the windshield cover of ALK. So we use it, and they use specific heating elements which are composed of ABS plus carbon nanotube. They are integrated in the structure, and we have a thermocouple. We want to simulate the de-icing effect. So the de-icing effect is very complicated to take account because we have to integrate a thermal electrical modelization plus the evolution of the ice. But we cannot do this with the thermal electrical modelization. So to integrate the evolution of ice, we need to declare another coupled Eulerian-Lagrangian modelization. But this coupled Eulerian-Lagrangian modelization takes many more time than thermal electrical modelization. So today the simulations are in progress, and we focus only on thermal electric simulation. So we make before a small test on small area. So here you can see small parts in ABS in the green parts. In red we have the copper electrode, and in white we have the heating element. We put different voltage. And we have four cases. The difference between the case, we have the initial case at the upper on the left side. On the left on the downside, we integrate steel screw, and at the upper of the right side, we increase the heating element. Here we can see a zoom of what we want to integrate. The idea is to see if the screw has got an influence in the modelization, if we take or don't take account this phenomenon, these parts. What we see, we have the same evolution of potential. We have a current density which are the same level, even though in the heating element it is not the same. So, and which is very interesting, it is the evolution of temperature in the heating element. We see we have the same effect if we take or don't take account the screw, so no problem. We don't take account the screw during the modelization of the real demonstrator. It is easier to do it. But we see if we increase the thickness of heating element, we have a very huge influence of the temperature in this case. So now we make this modelization of the real parts, like ALK sent us. So here you can see the position of different heating elements, the copper electrode. Here you have the view of meshing, so tetrahedral mesh for the parts and prismatic mesh for heating on copper electrode. We integrate the different potential of 48 voltage, and we make a variation that ALK and SETMA send us. And we see the evolution of the current density, and you have the upper and bottom temperature which evolve. So here you can see a little video show this variation of temperature, and here at the right you see when we put the voltage and we deactivate it, and we see the interest of we see what the evolution do on the temperature of the thermal field. To finish, we do the same thing with the final demonstrator with the battery filling system of SETMA. We integrate, like Andrea showed you before, the same system. So we make the simulation. We focus on the first part, which called part A. We integrate a specific, we represent in modelization the electrical cable with copper. We integrate 18 elements and we put 24 voltage on the 0 voltage at the other pipe. And when we do this, we see the evolution of electrical potential. We put the temperature on the current density. What is important, it is we integrate a user subroutine to make the same thing like SETMA do with a coupling control of voltage in function of thermal field. In our case, we don't put ice, so we don't correlate with SETMA experimental data. So after we will add the ice and we hope to make a good correlation. But the idea is to say here, in our case, we put a specific user subroutine to control the switching on and off the electrical potential. And if the temperature is upper 100 degrees Celsius, we stop the current. And if it is under 48 degrees Celsius, we start the current. And we can see the evolution of the system, and we can see it works. So the conclusion is we see that it is very important to integrate the different scale level to the modelization to take account all phenomena. So we see at the nanoscale modeling, which is very difficult to modelize, we have some different kind of modelization. Some of them are more precise, like dynamic molecular that Guita showed before, and the other are with the analytical model are very quickest and can give us a small idea of thermal and electrical conductivity. After we integrate the Joule effect and piezoresistive effect at the micro scale and macro scale effect to modelize different systems like de-icing, self-sensing, and self-curing. And we focus today to validate this modelization on the real demonstrator. So thank you for your attention. Sorry for my English because it is very awful, so sorry for that. And if you have some questions, don't hesitate. Thank you very much.
Thank you very much, Patrick. I don't know if there are any questions. You are free to ask them. Otherwise, we can have now a 15 minutes break and be back at 11 o'clock. If that's okay with you.
Thank you.
Okay, thank you.
Thank you.
See you later.
See you later.
See you later.
See you later.
Okay, hope everybody is back. So we can continue. We covered the first two sessions of the workshop, and now we are going to present the demonstrators developed within MASTRO. And the first presentation will be made by Matthew Collinson from AMRC, and it's about high-performance smart composites for use in aerospace and automotive applications.
Thank you. Hi there, I'm Matthew Collinson from the Advanced Manufacturing Research Centre, the AMRC, which is part of the University of Sheffield. I'm going to talk about my involvement in the MASTRO project, where we're coming from the perspective from mainly an aerospace, but also automotive use cases. We're going to quickly talk about the presentation contents. I've got a 50-minute slot. Hopefully it won't take that long. I'm looking for 40 minutes maybe, and then some questions at the end. So a bit about the presentation content. So talk about the AMRC, who we are, kind of what angle we're coming from as a research institution, and then a bit about the technologies developed and why they're needed at all. So we've got anti-static protection, self-cure, anti-icing, and self-sensing, and then a bit about the demonstrators, which is the main part of this. So we've got the leading edge, engine air intake, which are the aerospace ones, a car bumper, and then a fuel system, which is also an aerospace one. And then a bit at the end, a short section on the evaluation of these smart functionalities, how they're tested. So firstly, a bit about where I work, the AMRC, established in 2001, originally a collaboration between Boeing and the University of Sheffield. But nowadays, we work with almost anyone. We work with Airbus, Rolls-Royce, BAE, and also SMEs as well, small, medium enterprises. And we help manufacturers become more competitive, looking at new manufacturing methods, technologies, and processes. We've got a wide range of expertise now. We started off with machining, but we do automation, robotics, castings, additive manufacturing, composites, so a whole range of things. As you might have twigged, I'm from the Composite Centre, as this is a composite-based project. So a little bit about the Composite Centre and what we do as well. We've got 5 main research themes. So automated production. This is trying to replace or the labour-intensive manufacturing process that happens in composite manufacture. The machining of composites, very different to metallics, so it requires its own research stream. Advanced curing, looking at alternative methods opposed to oven curing or autoclave curing for composite materials, and that's where this project fits in mainly. Another one is novel materials and processes, so looking at alternatives to your traditional carbon fiber or glass fiber products. So that's where also MASTRO fits in with the carbon nanotubes and processes with the self-sensing and anti-icing. And then the last one is dry fiber processes, which is a manipulation of the dry fiber before it goes into the composite. So you can see, for example, our Dobby loom there. We've got Jacquard 3D loom as well, braiders, stitching, things like that as well. So a whole range of composite technologies. So first, I'm going to give a bit of background on the MASTRO smart functionalities. As you've heard previously, all the functionalities developed depend on the conductivity of your composite. So whether that be a matrix, we've talked about introducing the carbon nanotubes into that, or the carbon fibers that already exist in many aerospace composites. So like it says here, aerospace has an advantage of it's got the carbon fibers in the product already in most cases. However, accessing them, it's surrounded usually by an epoxy resin or the fuel tank case, PPS thermoplastic, and these are both electrically insulating by nature. And if you just try use the carbon fibers as your kind of electrical component, then these insulating materials are going to get in the way. But at this stage, we're looking at kind of aerospace products, not just the material systems. So I'm going to talk about developing kind of systems alongside the materials. And these systems were developed with the inputs from Embraer, who's a partner on the project. And a bit about what electrical devices fit into which functionality. So we've got anti-static, which Andrea mentioned already. It's low surface conductivity. Self-cure and anti-icing. These both use a resistive dual effect heating, as also previously mentioned. And then self-sensing, conductivity monitoring, piezo-resistive effect, which is a change to strain, and then the any fibers that might break due to damage. However, I'll go into these in more detail in their own sections. So the first functionality which I'll talk about is anti-static protection. So this has previously been talked about already, so I'll try to give an aerospace angle on it. So anti-static fuel pipes in an aircraft, aluminium fuel pipes would be standard. They already have anti-static protection being metallic. However, if you just want to replace them directly with a carbon fiber or glass fiber composite, for example, you won't have that anti-static protection due to the insulating matrix. So any static that's generated from either fuel flow or movement within the aircraft, things rubbing against each other, it won't be able to dissipate with a traditional composite. So the introduction of conductive particles will make the surface conductive, as previously mentioned. So as you can see from there, the surface resistivity is low enough to have self-protection from electrostatic dissipation. So the component here was manufactured. The idea was that we used an organosheet. As you saw previously, it was manufactured using thermoplastic and the carbon fiber in the press. Not only this fitted well with what was available at the time, it's a really good processing method. It can be used in a wide variety of components, not just the kind of fuel system that you saw there, but it could be pressed into almost anything at high rates as well. So if you get lots of these organosheets, they can just go through the press very quickly. However, it also opens up opportunities for other things as well. So not only an anti-static fuel system, as mentioned, you can modify the conductivity further to suit electromagnetic interference protection. Say, if you wanted to make a case for some sort of sensitive electronics, if you wanted to protect them, for example. So it allows for movement in what you're manufacturing. However, so you saw that the fuel system was made up of kind of box sections welded together, and this isn't the ideal way to manufacture that, we know. So I'm going to briefly talk about kind of what would be ideal in the future. So what we've done so far, we've proven that the concept works and the material is suitable for this use case. However, the manufacturing process maybe isn't quite there yet. What we'd love to do is manufacture it into a tape, carbon fiber, carbon nanotube, thermoplastic tape. However, the equipment to manufacture this, a continuous compression molding, as seen at the bottom there, wasn't available for this project. However, the material has shown that it is possible to use for anti-static. So if we had this available, what we'd do is we'd manufacture a continuous tape, and then you'd be able to use it in filament winding or tape laying, such as AFP applications. This would be more suited for a fuel system, could be filament wound into a pipe or a tank more easily. Along with the ease of manufacture, there's a potential for less wastage as you don't have to trim your parts. Lower capital expenditure, lower initial cost, as a press is more expensive than a filament winding machine in some cases, and overall it's a simpler production. So that's a brief overview of the anti-static fuel system. I'm going to move on to the second functionality now, which is self-curing. Firstly, a little bit of background about curing of thermoset composites in aerospace. Autoclave is the aerospace standard. you apply heat and you apply high pressure to your component. So you can cure a component and consolidate it really well. You get really good quality parts, and that's why it's an aerospace standard and consistently as well. However, there are some downsides. You have really, really long cycle times. You can only fit a few components in your autoclave. Autoclaves are expensive to start off with, limiting the use, who can use them. And also your part size is limited by your autoclave. If you bought an autoclave for a certain product to manufacture, and then you want to, say, increase the size of your part, you're limited by having to buy another autoclave. So a couple of negatives about existing composite production, and then I'll talk about self-curing now, the new kind of curing method that we've developed. So simply, you can see in the picture in the bottom right that it's a bit more complex than this, but this demonstrates it well. You connect your carbon fiber composite up to a power supply, run current through the fibers. They act as a heating element to heat the carbon fiber up to cure temperature. So this is very similar to some of the anti-icing that you've seen previously in some of the previous presentations. However, there are some more challenges. So there's higher temperatures. Cure temperatures in aerospace are up to 200 degrees. The ones that we used in this project are about 180. Larger geometries as well. We're looking at having to cure. We'd like to expand it from lab scale to a component that a manufacturer would actually be able to produce. So we're looking at 2-meter long sections. And we're not only trying to heat up in an area where there might be ice, it has to be heating up the whole component evenly. You want an even degree of cure over your component, which will reduce internal stresses, the final part. If you have an imbalance in your internal stresses, then you might get warping and your part geometry won't be correct. And this is particularly important in aerospace. So this isn't just material development at this stage, it's a whole process. There's lots of things to consider. So how do you connect your electrodes to your, how do you get your current into your component? Which electrode material do you use? You got to consider your tooling type. You can't use metallic tooling anymore, as it would short the electrical path. And also the insulation. A metallic tool will just suck all your heat out of your part. So you need to think of something that's thermally insulating as well. And then lastly, how do you monitor the cure? How do you monitor that it's you're getting an even cure all over your part, and how do you control it as well? So I've talked about some of the challenges. Now I'll talk about some of the benefits and why we're pursuing this. So previous studies have shown that there's a potential for reduction in void content compared to autoclave, because you're heating the component from inside out rather than outside in, compared to an oven, which heats in that way. It allows the voids to escape during the heating process when the viscosity is dropped in the resin. There's potential for quicker cure times. As you don't have to heat up the entire heating chamber like you would in an oven, you're heating up only the component that needs to be heated up. You can increase the heating rate by just putting as much power in as your power supply will allow. And also it allows for more controllable heating. If you have an exotherm, you can turn the power off at the source. Lower energy usage. Again, because you don't have to heat up everything around the composite as well as the composite, you get lower energy usage. For example, in our testing for a 2-meter long component, we've managed to use 1% of the energy compared to an oven cure over the whole cure. And then again, lower capital expenditure, the lower initial costs. The power supply that we used in this project was about £1,500. A good composite curing oven will run you into £10,000–20,000 and maybe more for a large component. And an autoclave could be up to 100,000, 200,000 or more, depending on the size of your component and the pressures that you need. So a much lower initial cost, much more accessible potentially. And then again, the size of the component isn't necessarily limited by your curing method. So if you need to manufacture something longer than your oven, then all you need is longer cables. But one thing that we wanted to do when developing self-curing is there are lots of kind of caveats that you might have to, things that you might have to change to use this new curing method, but we wanted to reduce those as much as possible. We don't want you to have to change your layup or what you're doing depending on the curing method. So what does a typical setup look like? This is a kind of standard, this is exposed to show you what's going on. You got your composite in the center. You can see, I think this is pre-preg laid up on a flat plate. You've got your normal kind of tacky tape and vacuum bag, vacuum pump. We've got breather. It's only around the edge here to show you what's going on. And then what's different is you've got these electrodes, and the current runs from one side to the other using the fibers directly connected as the heating elements. And then obviously you've got the wires out of the bag to keep the vacuum. And then the last one here is a thermocouple in the center to monitor the temperature. And then this is running on a PID loop to control the power going into the component depending on the set temperature. So the theory is quite simple. And this is an example of how it works. This is the thermal image of, I'm pretty sure it's the same part. However, so you might be able to see now some of the issues that start appearing with this type of heating. So to start off with, as mentioned previously, you get localized heating around the contacts, which isn't good for when you want to cure evenly. And another one as well is the temperature differential from top to bottom. You've got your hot spot in the middle here, which is indicated 87 in this example, and then your lowest temperature points are at the edge of the panel, so you get temperature drop off about 10 degrees in this case. So this is something else that we have to manage. So how we've kind of tried to fix some of these challenges. So the electrode position, depending on where you put it, you either get burning or you get uncured composite. If you have it too far to the left, in this example, you'd have a small surface area, and then that would lead to high contact resistance and lead to burning, which we've had here. You can see in this example. And if you have it too far to the other side, then you'll have uncured material on the left. So getting this contact size and position is quite important. Something as we scale up, as the size increase, the power requirements do as well. So we realized insulation was required not only on the tool that it was being laid up onto, but you required insulation on top. We use ceramic rock wool. It's really good insulator, forms well, and high temperature range up to 1200 degrees. So there should be no issue in any burning. And another one that I mentioned, temperature delta, temperature difference over the panel. You see in the bottom right here, we set up a small panel with thermocouples 1 centimeter apart from each other from the center to the edge. We ran the cure, and you can see here from the center to the edge, you get a large temperature drop off. This is exaggerated in this example as no insulation was used, but you can see it's almost exponential. So this is another problem that we had to solve. And then last one, the initial development was on pre-preg, and then we had to introduce it to infusion as well, as one of the demonstrators was manufactured using infusion. And this introduces further complications as well. How do you heat up dry fiber? How do you keep it in place before the cure with the electrodes? How do you stop the electrodes getting all gunged up with the resin, things like that? So another challenge there. So I'll stop with the self-curing for a moment. I'm going to talk about the self-de-icing. It's a similar heating technology as its dual effect, and it's using composites as well. But a bit of background why we need it. basically, aircraft are moving towards electrification systems, especially as we're looking towards electric engines within aircraft. Existing systems that use hot bleed air from a jet turbine can no longer be used, so they have to be replaced with an electric system. Not just anti-icing systems, but all these ones listed here. So electromechanical actuators, braking systems, things like that rely on either hot air or pneumatic systems. So one of them targeted here is electrical ice protection. And so this is why we're doing this. So this is an example setup, a small test that we did. It's a very similar method to self-cure. So again, we've got a composite with our electrodes on each side. This is a glass ply acting as a dielectric insulating layer. This example here uses unidirectional fiber, so we get a very distinct heating zone. And you don't have the temperature drop off like you saw in the previous example, which used plain weave. We used plain weave in the self-cure example as it was one of those ones that we didn't want to change the layup depending on the curing method. So we used a difficult or more difficult material potentially to show that the technology can work. So a bit back to anti-icing. Again, dual heating. Some of the benefits compared to using metallic heater mat that are used in some cases. The fact is that the carbon fiber used is still a structural component, whereas a metallic heater mat doesn't actually add any structural benefit to the component that you're adding it to. It just adds parasitic weight. So in this example, we've got the electrodes again, very simply, and then you can see here, big head connectors are just placed on there. These are typical composite fasteners, but we've used them as electrodes in this case. In this example as well, it's just one heating zone. As you can see here, one heating zone. This is a reverse side when it's connected up for a test. But you can do multiple zones depending on how you lay it up, and you'll see later on in the demonstrator how we do this. So this is the test setup, and then this is a thermal image. I think the set temperature was 40 degrees, and you get a much better, I think there's like 4 degrees difference compared to the center to the edge, so much better than our self-curing. And then lastly, the development on self-sensing. A little bit of background as to why we need this. The video that you can hopefully see on the right-hand side shows an impact into a composite, a carbon fiber composite. And as you can see, there's very little damage on the surface. It looks like a scratch at best. However, because the way the composite bends downwards, most of the damage will actually be on the reverse side, which is a common issue with composites, and it's called barely visible impact damage. As you can see from the surface, it looks maybe like a scratch. However, on the reverse side, there could be quite a lot of fiber breakage, which could lead to more damage developing in the future. So we wanted to develop a system that can detect this type of damage. So why is it needed? Obviously, you can't visually inspect it if it's not visible on the surface that has been impacted. There are methods out there, so ultrasonic C-scan. It's very good at detecting it. However, expertise is required to use it, and it's not very easily scalable to large structures, especially with small defects. You can use ultrasonic kind of tap testing or passive ultrasonic detection. This will tell you that there is damage, but it'll give you little data on the defect, or it's difficult to get calibrated information on the defect. You can include strain gauges on your part or fiber brags within your layup. However, these systems tend to be quite expensive, particularly fiber brag. So the self-sensing system that we want to develop, or we have developed, we want to have multiple levels of impact detection. First, we want to know, has damage occurred at all on any part of the component. Has there been a response to the system? Secondly, where is the damage? If it can tell us where the damage is on a full aircraft wing within 10 to 20 centimeters, look in this area, that'd be great. And then also, how large is the impact? Is it a small impact like this, or is it much more significant? So a bit about the background there. Now how the self-sensing system that we developed works. So you start off with your carbon fiber. In this case, it's pre-preg, but we've worked it on dry fiber as well. You position your copper electrodes at each end of the composite. This gives you your ability to monitor the resistance. So you monitor the resistance before damage, and then you get a set of data of a good composite before you either do this at the manufacture stage or just before it goes into service. You're using your composite, be that on an aircraft wing or something, you get an impact or you get excessive strain during service. You monitor the resistance again. So this can either be a continuous cycle of monitoring the resistance so you can see the impact in real time, or during takeoff and landing. And then this resistance data can be interpreted as damage. So once an impact has occurred, you will have either permanent deformation, which will induce the piezo-resistive effect to give an increase in resistance, or fibers will be broken, which are the conductive channels that you have. When the amount of conductive channels are reduced, you'll see an increase in resistance. And then because you're monitoring it along the side of your component, it relates to a position and you can see where the damage is. So this is a background behind it. I'm going to tell you how we scaled it up now. So we manufactured this PCB that allowed you to monitor the electrical conductivity in loads of different areas. So we could do in X and Y, like you saw in that previous example. We also had electrodes in the center. If you had a large wing, for example, if you wanted to do it end to end, and a small piece of damage occurred, it's unlikely to be detected. So you need electrodes in the center as well. This is just on a small panel. We used aerospace pre-preg. As you can see there, it's now laid up onto the component. And then we connected it to something called a PXI, which is a test and control computer. What we could do here is it had a multimeter which could monitor the resistance, and then we had an automatic switching multiplexer which allowed you to monitor pretty much between any of the points that you saw on that PCB. So there's a good chance of hopefully picking up the damage. And then to test it, we used the drop tower, as you saw in that previous video. We did barely visible impact damage, or BVID, and then we also punctured it. So 2 scenarios. Hopefully with the punctured, we'd definitely see some resistance change, and with the BVID, there'll be slightly less resistance change. Just to give a bit more context about how the scanning worked, we did a couple of methods, but there's 2 here that work really well, and this kind of shows you how we monitor we monitored them. So as you can see here, it does a scan over the whole panel, and then you can see which zone that the resistance change might be, and then you can kind of isolate which zone it will be in visually from the electrode position. So this one we nicknamed, I think it was 2-point scan mode, and then the second one, which uses something called 4-point resistance measuring, which is more accurate. Doesn't take into account the contact resistance of the electrodes. However, it's a smaller scanning area, however, should be more accurate. So some quick results. We did this graph kind of is a visualization of where the area where there was resistance change. And we've got 2 panels that we've got in this example. We put the PCB in the mid-ply of the layup and at the bottom of the layup. as I mentioned before, the damage is more likely to occur on the bottom side of the impact. So we thought we'll see, hopefully there'll be a better response from there. As you can see here, it managed to detect on the bottom ply more accurately for BVID. It detected some change, but not in the correct position for the middle ply. And then both of them managed to accurately distinguish when it was punctured. There was a big resistance change. So it's possible to monitor barely visible impact damage using this method. So this was a 2-point zone, and then we tried the more accurate mode as well, the 4-point zone. As you can see, bit of a mixed message from the barely visible impact damage. The resistance change wasn't enough to be detected in using this method. However, for puncture, you can see a large single point of impact was detected in both cases. So as you saw, that PCB was the size of the component. This isn't practical when scaling up. You can't make a flexible PCB the size of a wing. It's not necessary either. We manufactured strips of PCBs. This is the trace of it. And therefore you can put as many of these in your component as you like, lined up next to each other. So in our 2-meter long wing, we can put these next to each other as required. This is an example of it in the layup before being infused. And then this is the example afterwards. And then you just have your little connectors soldered on in the same way. However, not requiring a huge PCB to be in your layup. And then I'll talk about how this will fit in the demonstrator later. So here are the 3 demonstrators that the AMRC was involved in. These 3 were all self-cured. We had and also shared the same tooling, which I'll talk about in a minute. But to start off with, we've got the leading edge. This was vacuum-assisted resin transfer molded or infusion effectively. This one had all the smart functionalities in it, so it's self-cured. There's anti-icing, self-sensing included. We understand that infusion isn't always used in aerospace, but we wanted to show what you could do if you were more flexible with your manufacturing method. So we used dry fiber, Huntsman infusion resin with 180-degree cure temperature. The second one, the example was an engine air intake. We used standard aerospace prepreg, and this represented a more kind of standard aerospace component that might be in use right now, rather than something that's a bit more not used at the moment. So standard aerospace prepreg, again, 180-degree curing cycle, and in this one we put in the anti-icing functionality. That was the main one for the air intake. And then last was a car bumper, which is manufactured with infusion in a similar way to the leading edge. So as you can see there, it doesn't really look like a car bumper. We were unable to obtain a car bumper tooling, so we modified the leading edge to insert these a space for light and an air intake. However, this didn't make the curing any easier. As we made these holes, it actually cut out the conductive channels that you need for dual heating, so it increased the challenge for us on this one. So we self-cured it at 120 degrees, and we also included the self-sensing functionality. And the idea with this, with self-curing anyway, it showed you could use a variety of materials, geometries from different industries, and also including all the smart functionalities that we've developed. So now I'll show you some images from the demonstrators that we manufactured and hopefully give you a bit more context. So this was the tooling that we manufactured. We did glass fiber tooling with a PTFE layer to give a good releasing surface finish. This is it set up. This is a tooling set up ready to go for an infusion. You can see on the outside there the rock wool applied for the insulation, and then the self-curing system at the back. Unfortunately, I haven't detailed it a lot, but you see the wires coming out of it attaching to the component as required. So that's a bit about the tooling used. I'll talk about how we did the layup, which is similar for all three demonstrators, but I'll talk about first the anti-icing. So this shows you kind of the 3 steps that we did. This is in the leading edge. So the first ply was glass fiber. You put down your copper strip on the right there, and then the second step would be kind of painting on your carbon nanotube resin, which allows for a good for low conductivity contact to the carbon fiber, which you can see in the third in the center point. For the demonstrators, the first 2 aerospace ones, this is the anti-icing. We had 3 heating zones. You know, the central large one for your main impact point on the right on the leading edge, and then 2 ancillary heaters as well for heating up any runoff ice. This is on the first ply as well because we wanted the heating source to be as close to the ice as possible. And there you can see it laid up fully to the end of the component. And this stage is the same for both the first and second one. A few more layup photos. So on the left there, you can see the dry fiber laid up into the tool for the full length as well. We've got the copper electrodes for the self-cure there. And then you can see the big heads poking through, which allow for the contact to the anti-icing, which will happen after the cure. And then here as well, you can see some of the pre-preg being laid up. Laying up into a leading edge tool is quite difficult. So having to use rollers and release films to help it through. And then lastly, for the aerospace ones, this is a typical infusion setup. However, it's got some modifications for the self-curing. So you can see the bolts there that go through the bag, which act as electrodes. We've got 3 in this case. We've also, you can just about see them, it's green on green, but there's thermocouples placed on the bag to monitor the temperature in various zones to make sure that we're not getting any underheating or overheating in these areas. Briefly, the automotive bumper. So you can see that the cutouts here that we put in, we silicone these in, and then we had to cut around the carbon to get this in and lay it up. And this is fully bagged, ready to be infused. So like I mentioned previously, the conductive channels are now cut, and dual effect heating can't happen in that central layer from the close end to the far end where the blocks are, and therefore the middle parts wouldn't be reaching temperature. So to alleviate this, we used copper sheeting on top of the fusion mesh, and this acted as a heat transfer medium just to help the heat reach the center. And lastly, some kind of final pictures. All these 3 components were manufactured late last month, so it's got quite hot off the press. So these are what they look like at the moment. They're just being kind of finished up and touched up to make them look a bit better. So you can see here on the left, these are what the aerospace ones look like. You can see the electrodes from the outside and the anti-icing heater mats. Something that I didn't mention as well, we also used a Nomex core in the aerospace demonstrators to show that self-cure is compatible with different type of materials. And then also at the bottom there, on the right, sorry, you can see the automotive one. Needs some touching up around the air intakes and lights. And then also, last thing is the self-sensing electrodes need to be applied on the back surface, and that'll be with using the carbon nanotube resin to ensure a low conductive contact from the electrode to the component for sensing. And a bit about the evaluation. I've talked a lot about the manufacturing and some of the developments that we've done, but do they actually work? So I'm going to put this graph on the screen. I'll talk you through it. So there's three main lines here. So the first one is thermocouple 4. This is the temperature of the control thermocouple. And I think this was for one of the aerospace demonstrators. So it went from 2 degrees a minute up to 120, and then 2 degrees a minute up to 160 in the post cure, which is fine. It managed to reach the temperature okay. The control systems for such a large component ensures it's a bit wobbly. However, we're more concerned about it reaching temperature rather than getting a good control system right now. The second part is the power going into the component, which is the red line, and the scale is on the right. The 1500 watts is the limit of the power supply, which it hit trying to raise up to 2 degrees a minute. But one of the good things is during the cure, so the first section of the cure, very little power is used as it's exotherming, and it's well insulated. You see there's very little temperature rise and no power usage. In the second stage where the exotherm has gone off, there's a little bit of power usage. Unfortunately, it's a bit spiky, but probably on average you're looking at 400, 500 watts for a large component like that. The last line that I'd briefly like to look at is the range of temperatures, which is the blue line here, and the scale is on the left. So the part had about 9 thermocouples on it, and this is the range of all the temperatures that were picked up. As you can see, the range got to about 30, 35 degrees during the cure for both the 120 degree cure and the 160 degree cure. This isn't, obviously we wanted lower than this for an aerospace component. It's something that we can continue to work on. However, this isn't the full picture. This is just what we picked up on the outside of the bag. So this is just a kind of quick snapshot into what we've done over the last 2 months of the project. We're going to be doing full DSC analysis on the component to see the degree of cure compared to an oven or autoclave, and also doing some microscopy, which hopefully we'll be able to share with you at the end of the project. For anti-icing, we are doing testing at a local university climatic chamber, which has the ability to simulate wind and rain. So what we've managed to do is you can see on the right there, it's an example of the ice buildup on an example wing that they had. So we're going to test the ability of the demonstrators to shed ice in a de-icing situation, so build up the ice and shed it off. And also preventative anti-icing, so just keeping the temperature above 0 of the wing to see if it can prevent ice buildup. The efficiency of the heating and the responsiveness will be evaluated, and hopefully if the testing is successful, it'll bring the technology to around TRL 5 or 6 as it is in a representative environment. And lastly, it's a self-sensing. The drop tower that I showed you previously was for quite small samples. Unfortunately, we can't fit a leading edge into that. However, most damage to a wing or an aircraft, which is kind of impact damage like that, will either be runway rash, which is stones kicking up during takeoff and landing, impacting the surface, or it could be something simple as maintenance, someone dropping a spanner onto the plane. So for our test, we'll be using more representative testing, so dropping either a ball bearing or something blunt like a spanner, and see if it can detect the damage in that way from a set height. So yeah, that's everything from me. Are there any questions?
Hello, I have a question.
Hello.
Hello, I'm Marceli from Acciona. A question regarding the electrical conditions of the self-curing process of the real elements that you show. What is the electrical conditions?
So like the voltage and amperage of the curing. Is that what you're wondering?
Yes.
So yeah, the power supply that we used was 1500 watts in total. Because the conductivity of carbon fiber is low, it's 150 amps is the current limit, and it's 0 to 30 volts. So yeah, it's high amperage, low current. Sorry, yeah, high current, low voltage. This also means that for the anti-icing, this is also the case, which isn't compatible with an aerospace system. However, if you increase the length and change the geometry of the carbon or the carbon nanotubes used, you'll be able to tune this to what is required for an aerospace system.
Okay. No more. Thank you.
Thanks.
Okay, are there any other questions for this presentation? Doesn't seem like that, so we can continue with the presentation about self-heating smart components for the automotive exterior applications. And this will be covered by Alki.
Yeah, hello. I'm going to share my screen. 1 second. One moment.
If you have trouble for sharing, I can share for you.
Yeah, 1 second. Okay, should be fine. Okay, do you see now?
Yes, perfect.
I put in full screen. Okay. So, okay. So, good morning, everybody. I'm going to cover one part connected to the automotive application of smart components developed within MASTRO, and try to give to make some reasoning behind the project outcome, being like an electric vehicle OEM. So a little bit a different perspective than the technical one already given in a very good way by Chetman earlier. So I think there is a microphone open.
Sì, però qua in questo momento stavo cercando un attimo.
Hello.
Ok.
Creare e niente, io poi dissi se potevo caricare con le voci di budget le cose del progetto qua.
I think that somebody from okay, thanks. So as Alke, we are a few words about the company. We are a European manufacturer of professional zero emission vehicle. We make electric vehicles since year 2000, so about 21 years of experience in the sector. We don't make passenger cars, so you are not going to see in the highway, but vehicles for professional use, logistics, transportation, and special application. They are sold in more than 40 countries, also outside Europe. And we have activated R&D oriented to innovative solution about materials, technologies, and self-driving solutions in the last period. Something about our background before Mastro that can be useful to understand also the reasoning behind. We were involved in another project finished about 2 years ago. That's Jospel. In this case, we were using smart materials for interiors and mainly oriented to optimizing the cooling and heating system inside the cabin with a final target of having energy optimization. In that project, we have developed heated floor, heated roof, heated side panels, and seats with some little bit of difference compared to the one that will be presented just after my presentation. In that case, was oriented mainly to heating, interiors, and the ICT platform was mixing remote activation and with a lower level of integration, let's say, with the present Mastro project. But that's good. This background because given us some elements also to work in the Mastro project. Alke at Mastro, we have worked providing free demonstrators, the cold cover, the windshield cold cover, the battery filling system, and door gasket that has been studied and well presented also by Chetma from the technical point of view evolution about the results earlier this morning. Looking to these free demonstrators, the one that is more useful to introduce the reason that we are making is the windshield cold cover. This is an item located, you see from with the arrows just below the windscreen. And is one place where during winter time you have deposit of snow or ice and can provide issues to the wiper functionality. So that's something that's a critical part for the vehicle itself. We have made a parallel demonstrator also in an looking to an automotive like a sport car. It has been performed the test by Diad within the project, and the problem is the same. The deposit of snow and ice in this part. That can be sometime dangerous. Why the icing smart functions for external bodyworks? So I have introduced one example. There are many others when looking also to our personal experience when having a car parked outside a building during the winter time. You have presence of ice every morning and sometimes also during the day that provide problems to the functionality itself of the vehicle, or sometimes the problem is not to be able to switch on the vehicle, but the accessibility to the cab. The example of the door gasket presented earlier is because if you have ice on the door gasket, sometime you can get problems on opening doors. The same for locks or other elements that maybe are not present in passenger cars, but in our case for professional vehicles, you have special panels, buttons panels outside the cabin that control external devices, and they can get frozen. So this possibility to have de-icing functions located in a specific area of the exterior part of the vehicle, the body mainly, can save time to the operators, and to help performing in a better way the task the vehicle is designed for. Some example of areas have been given. So the windshield cover, the door handles and locks. If you have a van body, you can have other doors on the rear part of the vehicle, the door gasket perimeter, the front and rear lights area. That can reduce the visibility, and other electrical or hydraulic power socket that are located in front or rear to the vehicle. Clearly, some of these items are not present in passenger cars, and they are specific for the kind of vehicle that we are developing and selling today. Why Alka as case study? We have many vehicles delivering some way critical areas, Scandinavia's country, Iceland, or other Nordic countries. And in such scenario, beside the problem that you can get for an electric vehicle with battery and so on, but the exterior is, let's say, the second topic that came back to us when we have some feedback from end users. The perspective of my comments are also looking some business point of view. Consider technical side has been already covered. Here you see few pictures of vehicle in real environments where these vehicles are used also for snow street cleaning, from the snow, ice, salt sprayer for the ice and so on. So they are active when other vehicles usually are stopped because of the weather, the critical weather. This is the demonstrator of the windshield cold cover developed within Mastro. The last picture below, you see here from the bottom side, let's say, and fully wired. In this case, this is located in the lower part because, of course, the place cannot be in contact with the snow, with the ice that melts and generate water that having current inside these plates can provide issues to the functionality of the system itself. Originally, the design of this item was planned to be fully integrated with a multi-layer design and done by vacuum forming of extruded sheets. We have done trials to follow the original way, but got some problems, and also because of problems given by the lockdown and so on, it was difficult to finalize that way with the further trials. And we have moved to an alternative solution in a way, anyway, looking anyway to demonstrate the approach that we had in mind, but using independent plates attached to the main ABS item. The component used here is the original windshield cold cover of an ITX3 electric vehicle. And this has been attached by adhesive and properly linked with wiring and connector for both the power supply, but also to link the system to the ICT platform, and behind it the cloud, the Mastro Cloud platform that will be described later, I think, early this afternoon by Pinouts. What happened? I told that would like to make a reasoning from the business point of view. The system, like it is today, works. To be industrialized and helpful for the automotive market, we believe that should be not something that you attach to the item, but like in the original idea, should be totally integrated in the component in a way that the OEM get the already let's say assembled item and have only to connect with the power supply, and in case the ICT network of the vehicle.
Ma me lo fai vedere il grafico?
There is an open microphone.
Sto con la
So taking in consideration the experience that we got from the project, we see two different ways, two different alternatives to make effective from the commercial point of view and the industrialization point of view of this kind of smart material usage oriented to the icing of exterior parts of the body of a vehicle. One is following the first option, is to work with a multi-layer approach when doing the production of the item, and in our opinion, this is the right way to follow when the full component needs to perform to deliver the icing property. This is probably more easy to be produced because you only add one layer. Critical things, but we'll see also later. This point is the connection with a power supply that must be considered at an earlier stage without delivering extra activity after the delivery of the finished component. The second scenario is looking to a patch approach, meaning that you have a larger item, a larger component, and you want to deliver these de-icing functionality in a limited part of this item because of power consumption, because of heating other part of this component can generate problems to the other elements near to the main items. I make the example: if you need to activate the de-icing in the door handle, of course you don't. For instance, we have like a plastic part in the door that cover the full length of the door. But if you need to work only in the door handle, of course you need to activate the de-icing only in the door handle area, and this could be the second approach. In this case, one alternative path could be to work in a way that you have the original item delivered with a traditional approach, with traditional process, and you add like a patch in the specific target area with a solution that can be deformable. So you can attach, and with a thermodeformable adhesive film. The idea is similar to the decals used for advertising on exteriors of cars. So you could apply specific in specific area this kind of film. Of course, this has been not studied within the project, but is a possible scenario, having in mind some specific uses, and of course the basic the outcome from MASTRO can help on that the development. Also in this case, the key aspect is the connectivity with a power supply. So the idea would be that first you attach the connectors in a way that it is easier, and after you make this film to match the round area surface that must be heated for the de-icing property. Some final comments. First, some key aspects to take care. First, the manufacturing process must be fully integrated. So one-shot item, meaning something that you get in an easy, not easy, but from a specific supplier without having 10 reworking after, or a large amount of labor to apply the different sub items. Like for instance, we have done during the project, but due to to what was available in terms of process. Second, power supply connectivity. During the project, the main problem was not really the surface that provided the heating, but at least from our the experience that we had within MASTRO, but the connectivity to bring the power supply, and most important, the electrical insulation, because of course there is circulation of current, and especially during the icing, where you have water around, you cannot put in direct contact this layer of heated plates because you have short circuits or problems in other areas of the vehicle. So this is not something that in a very early stage was considered, but during the project we have found this problem. Also because the component itself, even if it is like a, let's say, plastic component, but is fixed to a steel or a metallic, in general metallic frame that is conductive. So you need to totally isolate that kind of item for the right performance of the device itself, for safety, even if you have low current. So is not a risk for the operators, but anyway, there is a need to totally isolate the system. After, third is cost against benefit. Solution cannot be applied for any scenario. In some situation, to apply a much more sample resistance or other kind of solution already on the shelf maybe can provide a good result as well. So it is to focus on a specific solution where this scenario can be cost effective. Last considerations. Why these smart materials apply to electric vehicles? We found that there is a good match between these kind of technologies and an electric vehicle. First of all, because an electric vehicle by definition is powered by electricity, so you have large amount of electrical energy available for the functionality of the vehicle itself. And second, because of that, by nature, an electric vehicle is already integrated with a communication architecture that make much more easy the integration of smart functionalities in terms of IoT, ICT at ICT level. And this kind of integration makes smart much more easy to apply advanced programmable functionalities. I guess that also this afternoon in the Pinouts presentation, this topic will be covered. And to maximize the results that we can get, for instance, we found that the power supply of this kind of system made in a regular way give a worse result than having not continuous power supply. So this kind of change also in the activation of the different smart devices linked to centralized architecture can be more easy on board of an electric vehicle instead of like a traditional vehicle. That's all from my side. It is, of course, shorter than the ones from Matt just before, but all the technical topics have been largely covered by Andrea, by Chetma earlier. So I wanted to focus only in the business side, let's say, industrialization of this kind of solutions.
Okay, great. Thank you, Lamberto. Are there any questions for this presentation? It doesn't seem like that. So I think we can just continue with the next presentation, which is by Santi and Siteve, and they will present about self-heating textiles for automotive interior applications.
Can you see my screen?
Yes.
Lucia, are you there? Just a moment, please. Okay, I will start the presentation. I was waiting for my colleague Lucia, but I will do the first slides. Good morning, everyone. My name is Sofia Silva from Senti. So I will talk about self-heating textile for automotive interior.
Sorry.
Okay,
Sorry.
Lucia, go on, please.
I had a problem with my connection. Sorry. Okay. Textile, self-heating textile for automotive interior was on one of the research topics of MASTRO project, and will be presented by Sofia Silva and from Senti, and me from CITEV. So these are the topics of our presentation. We are going to take this opportunity to introduce you CITEV and Senti in brief. Then we'll show you a video that summarized performed work. After this, each step of R&D approach will be detailed by Sofia and me. And at the end, main conclusions of this work will be presented. So CITEV is the Portuguese Technological Center for the Textile and Clothing Industries. It is a private non-profit organization active since 1989, with facilities in Famalicão, near Oporto in Portugal. CITEV's mission is to support the technical and technological development of the textile and clothing industry, promoting innovation, inducing new capacities and competences, and helping on the definition of industrial public policies. CITEV Group includes CITEV Textile Technology, CENTI, and a technological professional training school called AFTEBI. Next, please. CITEV main areas of activity includes testing, product and process certification, research, technology development and engineering, sustainability and circular economy, manufacture digitalization and industry 4.0, product design and fashion intelligence, training and coaching, innovation and clusterization and intercluster cross fertilization, being the managing authority of the Portuguese textile cluster. Next, in this slide, we can see some annual figures. Working CITEV 140 people at full time. CITEV has 1,300 active customers, has more than 50 ongoing R&D projects, and about 100,000 tests are performed per year. So, Sophia, you can go on.
Thank you, Lucia. Sophia speaking again. I will start with a brief presentation of CENTI. CENTI is the Center of Nanotechnology and Smart Materials. This is an institute of new technology with a multi-sectorial orientation. CENTI is the result of a successful cooperation with 3 universities, 2 technological centers, and 1 institute of new technologies. Our main pillars comprise the functional materials and surface solution, the smart materials and system, and the design and engineering. Some facts and numbers. At this moment, CENTI has more than 145 researchers and more than 15 master and PhD students, about 170 ongoing projects, and a portfolio of more than 250 active clients. The next few minutes will be reserved for the self-heating textile promotional video.
Così.
Okay. Now, a little bit of our developments. The self-heating textile was conducted in 3 main steps: the conductive yarns development, textile fabric production, and prototype assembling. The self-heating textile demonstrator is a smart woven fabric based on melt spoon yarns for heating comfort performance in car seats. The target self-responsive functionality is self-heating through Joule effects. The target temperature was selected to 35 degrees. To control the heating temperature, an electronic off control was developed. To ensure the user security, the heating system turns off automatically when the target temperature is achieved. First step of these developments was the production of an electrically conductive compounds. Self-heating functionality through Joule effects has been achieved by the incorporation of electrically conductive carbon nanofillers into a thermoplastic polymer matrix. Thermal and rheological characterization was performed to evaluate the spinability of these compounds. Smart thermoplastic fibers with electrically conductive properties were developed through melt spinning technology. Our line allows us to produce several cross sections comprising up to 3 different materials. From the cross-section study, the one that maximized Joule effects was the sheet core. This geometry can be seen on this slide and presents an outside layer composed by electrical conductive compounds and a thermoplastic material on the core layer to promote mechanical properties. After the smart fiber production, a twisting step was employed. Fibers were twisted in a continuous trend. Usually this process is included to make fibers suitable for the textile process.
Several knitted samples were produced at the lab scale with the main purpose of validating of performance of developed fibers during the textile process. We can see some pictures of the equipment. Using the developed yarns in the project, smart plain weave fabrics with self-heating capacity through Joule effects were produced at pilot scale with collaboration of a Portuguese textile company called TMG. In this slide, we can see some pictures of the weaving process. The woven process, the woven fabric were produced following 5 different layouts. The different layouts were related with the electrode's position and distance on the fabric. A commercial yarn made of silver-coated polyamide was used as electrode. The most promising fabric was tested and characterized, and from the results analysis, it is possible to conclude that smart woven fabric presents good results regarding fogging and flammability, but mechanical properties need to be further improved. This can achieve through the combination of developed yarns with other yarns in a multi-layer structure approach.
After the smart fabric evaluation, these demonstrators were integrated on automotive parts. 2 car seats were used, one from Alke and a commercial seat to integrate the different woven fabric layouts. The smart woven fabric demonstrators were replaced for the original textiles on both car seats. In order to demonstrate the smart woven fabric functionality, this demonstrator was also integrated on a car armrests. For the armrest concepts, it was explored the smoothness and flow of the lines used in modern vehicles. The focus of this prototype was the temperature transmitted through the fabric. To do this, it was added warm lights around the perimeter. This is the armrest prototype. The armrest can be characterized by 2 distinct moments. While heating, the armrests show an orange intermittent light. When temperature reaches the target, the armrests show a continuous red light. A security system is activated when temperature reaches the targets and the prototype stops heating. The display attached can show the temperature of the armrest and the car seats. Thermal and electrical characterization was performed on prototypes for 10 minutes of heating. Performance evaluation for the commercial car seat show that applying a voltage of 28 volts, the smart oven fabric overpassed the target's temperature. Through the characterization performed on Alke seat and on the car armrests, it was possible to verify that applying a voltage of 18 volts, both prototypes overpassed the target's temperature. To make possible to heat through Joule effects on the smart fabric, an electronic off-control system was designed and incorporated on prototypes. This scheme is an overview of the electronic system. To perform the data visualization, a microprocessor was added, which has the functionality of presenting the data in real time through a graphical interface and is responsible for making an internet connection to the cloud through the ICT platform. Now, to demonstrate the prototype working, we prepare a short video. So at this time, we are turn on the electronic system. Here we can see the temperature increasing after the system turns on. It is possible to see the orange intermittent lights blinking during the fabric heating on the background image. At the moment the demonstrator reached 35 degrees, the electronic system turns off, temperature stop heating, and the LED turns on turns on a red fixed lights. So some conclusions. New self-heating oven fabric were developed and produced at pallet scale. These fabrics are based on in novel polymeric multi-component fibers developed under MASTRO projects, used as heating elements with tunable resistance for heating comforts performance in car seats and other car components. The performance evaluations show an increase on temperature through Joule effects that overpass 35 degrees, it was the target, with an applying voltage of 18 volts. So this is it for our side. Thank you very much.
Thank you very much to both of you. Are there any questions for the presentation of Santi and Citeve? Okay, I don't think so. So I think we can have now the lunch and meet again at 1 o'clock to continue with the next presentations. So see you at 1.
Okay, thank you.
Bye-bye.
Bye.
Bye.
Good break. Bye. Bye.
Bye.
Bye.
Lunch.
Buon appetito.
Bye.
Hello.
Hello. So is everybody back?
Soon, I suppose.
And yeah, the next presentation is from University of Alicante and is about smart concrete with self-strain sensing functionalities for civil engineering and architecture applications. So Pedro, you can proceed.
It's okay? It's okay?
Yes, we can see, yeah.
Okay. Good morning, everyone. My name is Pedro Garcés. And my presentation is entitled The Development of Smart Concrete with Self-Sensing and Heating Functionalities for Civil Engineering and Architecture Applications. Alicante University contributions to the MASTRO project has focused on the sensing and the icing function in concrete. It is widely known that the main function of concrete is its structural function. On the other hand, concrete, cement-based material in general, are dielectric, that is, bad conductors of electricity. However, the addition of a conductive common material such as graphite product, powder, carbon fiber, carbon nanofibers, carbon nanotubes, transform the resulting mixture into a conductive material. And it yields the possibility of using this new material for other functions different his structural one. So it can be considered a multifunctional compound. In MASTRO project, we have developed the strength sensing function, that is the ability of a structural material to detect its own deformation when subjected to some external load. And specific applications include structural vibration control, traffic monitoring, building safety, and structural surface monitoring. On the other hand, also we have developed the heating and de-icing function. It is implied that it's able to quickly melt the ice deposited. That is, it can be considered a curative process, or to prevent the ice formation from the freezing of the moisture of the roadway, so it can be considered a preventive process. Different actions have been carried out by Alicante University, some of them in close collaboration with other partners such as Applied Nano Solution or Acciona Group. First, specimens of Portland cement paste were manufactured with the addition of CNT and graphite products, or even the hybrid addition of both of them. Next, the dispersion of the CNTs and the mixture of both of them were optimized, very important and difficult process. And next, the percolation threshold was determined by the measuring of the volume electrical resistance of each specimen. Percolation threshold comes when there are enough carbon nanotubes to establish a continuous path of electricity. When this percolation threshold is reached, it makes no sense to increase anymore the amount of carbon nanotubes because the resistivity doesn't change significantly. Next, in order to evaluate the influence of the type and degree of oscillation of CNTs on mechanical and electrical properties, and also on strain sensing function of the conductive cement paste, different oscillation treatments, ozone, nitrate, sulfuric acid, or ozone and plus sodium hydroxide, were developed, were carried out, by the way, in close collaboration with Applied Nano Solutions. The sensing function is based on the change in electrical resistance in conductive cement-based material when some stress is applied to it. When a load is applied to a specimen or a structural element, the contact of carbon nanotubes, or even the carbon nanotube and cement matrix, became closer. and it implies a decrease in the resistivity level. Here we can observe the gauge factors of the sensing level and the resistivity and the compressive strength for different treatments. Is mainly noticeable the ozone treatment and sodium hydroxide functionalization, not only in the gauge factor that increased clearly, but also in the resistivity that decreased. Nevertheless, regarding the mechanical properties, no major variation were observed. Next, we studied the preparing the cell sensing behavior of hybrid CNTs 1%, C100 we used, and graphite product ABG 10, 5% added to the cement base. And it is clear that we are working within the elastic regime because stress and strain are extraordinarily reversible and proportional to the electrical resistivity. When the load is applied, the contact between carbon nanotube is more close, and the resistivity, the resistance, consequence, decrease. Therefore, by controlling his resistivity, its state chart and its structural field are checked. Next, we can observe the effect of the temperature on different parameters during the strain sensing test: electrical resistivity, elastic modulus, and gauge factor, so the sensing level, and also the Pearson coefficient. We can observe that there was not significant change in electrical resistivity increase with the temperature. The mechanical response was similar in all tests we can observe, so discarding any structural damage during the loading or heating processes. And on the contrary, a clear increasing trend was observed in the gauge factor upon heating, especially in the last temperature level. Next, we can observe the effect of train, so expressed at water saturation degree, on electrical resistance, on elastic modulus, and in the gauge factor, strain sensing level. We can observe that the electrical resistance presented a linear decreasing trend as the composite was trained. So it is clear that the prevalence of the electronic conduction. The elastic modulus decreased from about 15 gigapascal to 10 gigapascal. There were some cracks on the material surface after this temperature exposure. But the most important result of time was that the maximum gauge factor was obtained at 71% of water saturation degree. And taking into account that we can apply the water repellent paint at the surface, on the surface, it is very important in order to achieve the better conditions from the point of view of the sensitivity levels of our sensor. Next, we can observe the study of the sensing function of conductive cement-based sensors manufactured with the same page used in the points studied before, and then attached on the surface of a standard non-conductive concrete, so without any carbonation materials, in this case, a pillar. And the figure showed that it monitored the strain, the red line, of the concrete element in a cyclic vertical compression loading and unloading test. Correlation between electrical resistivity, the blue line, and the change in the strain of the concrete to be monitored can be observed. We should take into account that the electrical changes are in the sensor, not in the concrete. In the concrete, the changes are due to the strain, the deformation of the concrete. Very good, very interesting result. Also, a pretested concrete beam, it's in great color, here we can observe more clearly, has been used to study the effect of the steel reinforcements and bending behavior. In the beam, the same small sensors are attached on the surface, we can here, not only in the upper face, also in the lower one, and in order to compare the compressive and tensing compressive response. And again, very good correlation between mechanical and electrical resistance has been observed in both phases. Well, concerning the heating function in conductive cement paste, we can observe here the first results. Here is a sketch of the conductive cement paste specimen ready to be tested. And applying an electrical potential difference to the conductive cement matrix causes the heating of the materials by Joule effect, that is widely known. The temperature reached depends, of course, on the voltage applied. Here's 20 volts, that is 40 volts, which in turn presents small difference in the temperature when applying DC or AC voltage. Again, also we check the repeatability. That is the same behavior of one single specimen to different tests. It's very clear. And the reproducibility, the same behavior of different specimens, different batches to the same tests. That is very important in each and every experimental and project. Very, very important parameters. Next, in order to model the mechanics of heating, a previously used model was applied using the equation and parameters from the aforementioned model, and all the experimental tests has been simulated. The fitting level of both curves is significant, so the optimized conductive cement-based material could be determined by this tool by analyzing the minimum power required to obtain a desired temperature. Here it is shown the summary of the electrical characteristic resistivity current, current type, fixed voltage applied, temperature variation, and energy characteristics. The calculated cost is also included, not only for paste, conductive paste, but also for concrete specimen or were studied. Next is the study of the heating function, but in concrete, conductive concrete, also with the addition of CNTs and graphite products in the same dosage, in the same proportions. Also, the higher the voltage applied, the higher the temperature reached. And what is very important, the heat rate of time is higher with a higher voltage. Here, the figures show the evolution of the temperature of the conductive concrete specimen that was previously introduced in a freezer. So, being the ambient temperature and the surface of the concrete specimen of -15 Celsius degrees. Next, a power supply is to none, and the current through the concrete element, so the Joule effect, provokes the increment of the temperature above 0 Celsius degrees. It can be considered a curative test. Imagine a real runway in an airport, and with this applying a current, it is possible to keep the temperature in this ambient above 0 Celsius degrees, so the runway open, the airport open, not closed due to the bad conditions of weather. And this figure shows the evolution of temperature of the concrete element controlled by a thermal test. when the concrete reach values approximately of plus 5 Celsius degrees, in a snowstorm, and the temperature decreases quickly. And then the power source is connected at its voltage, maintaining constant the temperature in spite of being the ambient temperature of minus 15 Celsius degrees. Next, concerning the demonstrated prototypes transport infrastructure sectors, the University of Alicante, in close collaboration with Acciona Group, have led along paving cell sensing and heating demonstration that consists of a 2 by 1 by 0.05 cubic meters slab of conductive concrete pavement. Regarding the heating function, we can observe here the concrete slab. In this case, it is fabricated added 5% of graphite products related to cement mass. I repeat that this experimental product is being developed in close collaboration with Acciona. In this case, 2 carbon fiber mesh were placed on the top of the first and second layer, respectively. Here we can observe the result at the beginning, only 5 Celsius degrees, and at the end, more or less 12 increment of temperature of 12 Celsius degrees. Concerning the sensing function, in this case, as fiber mesh placed on the top of the first layer as structural reinforcement, and this is the finished surface. Next, and in the upper side, we can observe the electrode placement, and also the strain gauge in order to check the strain, the deformation of the slabs. This is simply supported slab ready to be tested. And here we can observe the experience, in this case with the strain gauge attached to the upper face, so controlling the deformation of the upper face, that is the compressive response. And this figure corresponds to a strain gauge attached to the lower face, so tensile response. And when the load is initiated, the stress increase, that is the purple line. The deformation also increase, and as a consequence, a proportional decrease of the electrical resistance, orange line, can be observed. And also on the same behavior, but opposite in the lower face, of course, here working and bending. It is important that the whole structure, to say that the whole structure is a conducting material, so it is bulk setup, carbon nanotube and graphite product added to the mix as a part of the concrete dosage. So, concerning the prototype transport infrastructure sectors, we can conclude that the development of the strain sensing and heating and de-icing function has been achieved in the slab of conductive concrete pavements. Thank you very much for your attention.
Thank you, Pedro, for this presentation. Are there any questions? Okay, I think we can proceed with the last demo of today, which is covered by Acciona.
Okay, I'm going to share my screen. 1 second. Well, good morning, good afternoon, sorry everyone. I'm going to present one of the demos in which Acciona was involved in this master project, that is the design of a smart asphalt pavement. This work was carried out in close collaboration with the Roads and ITC group of the Innovation and Technological Center of Acciona Construction, and also in close collaboration with the partners of Applied Nano Solution, Arkema, and Superior Graphite. Now, just a few words about Acciona company. Acciona has more than 11,000 employees distributed around of 30 countries. The main business areas are infrastructure, service, energy, and water. The master project is coordinated by Acciona, by the new materials group of the Innovation Center of Acciona Construction, that belongs to the infrastructure business area. In this, throughout this presentation, I will give a brief overview of the asphalt matrix demonstrator, including the self-functionality developed and the physical principle they are based on. After, I will summarize a bit the pavement design and the validation strategies followed. And finally, I'll share some results for the self-de-icing demo. The asphalt matrix demonstrator developed in Mastro includes three self-functionalities: self-sensing, healing, and de-icing. These three self-functionalities will validate it through two demonstrators. The first one was focused on providing a structural health monitoring and maintenance, preventive maintenance. And the second one is focused on prevent ice and snow on roads and enhance the road safety. These self-functionalities were achieved by incorporating electrical conductive nanomaterials like carbon nanotubes and graphite-based materials into asphalt formulation. These functionalities are based on two physical phenomena: the piezoresistivity, that is defined as the variation of electrical resistivity of a material when a mechanical strain is applied. This is linked with the self-sensing functionality. And the Joule effect, that is defined as the heating that occurs when an electric current flows through a resistance. And this is linked with the self-heating functionality, in turn with the healing and self-de-icing functionalities. The pavement design is common for the three self-functionality developed and consists of a slab of asphalt pavement divided in three sub-layers. The top layer, or the wearing course layer, is made of pristine asphalt. In the middle, we place the conductive Mastro layer. And finally, in the base, on the bottom part, we have the other pristine asphalt layer. Between the electrode of carbon fiber grids are placed in the interlayer between the two pristine asphalt layers and the intermediate layer conductive. The bitumen formulation was developed using a 7100 bitumen, commonly used for a civil infrastructure. The results obtained along the project show that the incorporation of mixtures of coke together with expanded graphite results to highest electrical conductivity. After that, conductive asphalt mixtures were obtained using an asphalt concrete type, AC16. The number 16 refers to the maximum particle size of the aggregate. The optimum bitumen content was set around the 6%, and as aggregate were siliceous and limestone were used. As I mentioned before, as the asphalt conductive layer is the element that acts as sensitive and heating element. In around the 60s, using cables as electric heating elements were popular in manufacture this type of anti-icing pavement. However, this type of solution has the disadvantages that the repeated traffic loading may cause damage to the cable, so the system will become inefficient. MASTRO solution avoid this issue as the pavement is set as heating element. As electrodes, we are using carbon fiber grids placed parallel to the road surface. This approach allows how to simplify the upscaling process because this kind of grids can be roll and unroll, so it's easier to place on the pavement, and also allows to reduce the electrical power consumption because allows how to reduce the distance between the electrode. This point is very important in the case of the asphalt pavements because the conductivity is very low compared, for example, with concrete pavements. So it's critical to reduce as much as possible the distance between the electrodes to optimize the power consumption. Carbon fiber grids provided by BAS and Solidian companies were tested to determine the most suitable one. These grids can grow by flexible grids that are the ones supplied by BAS and rigid grids that were supplied by Solidian. You can see some pictures on the bottom of these grids as a sample. Among others, the heating capacity and the piezo-resistive response of each candidate electrode was analyzed to select the most suitable one. In the couple of pictures on the top, you can see an example of the heating capacity test. And on the other couple of pictures, you can see an example of the piezo-resistive test to choose the most suitable grid that I said before. Regarding the heating capacity, the grid labeled as S2 seems to be the most easy to handle, and the heating rate was a bit higher than the flexible grids. Regarding to the piezo-resistive response, no remarkable difference was observed between the different grid types. Although each grid seems to be a bit more sensitive than the other ones. Based on the previous results, the rigid carbon fiber grid labeled S2 was selected to be used as electrode in the demo case. The validation strategies followed might be divided in two main cases: sensing and heating, that includes healing and de-icing. The self-sensing validation strategy consists on applying a proper load condition on the slab to generate crack inside the pavement. And simultaneously, the pavement is monitored, measuring the electrical resistance change. Using the same slab that we have previously cracked, heat is applied to heal the pavement. Along the project, we have obtained that a temperature around 60 degrees is enough to heal the pavement. And after the healing, the pavement is loaded again and monitored to evaluate the mechanical performance recovery after healing. In the case of the de-icing, well, the two approaches could be followed to prevent the icing on the road, or to promote the melting on the ice. In this case, due to the pandemic situation, the demo was expected, in principle, the demo was expected to be carried out during winter, but after the extension of the project, we had to carry out it in summer and indoors. So finally, we decided to follow an approach of study the melting rate of the ice placed on the pavement surface. So In this slide, you can see some pictures of the manufacturing process of the demo. The first step was to place on the bottom of the mold. Okay, we are using a mold, the pristine asphalt mixture. After that, we place the both carbon grids that are used as electrodes and the conductive layer. And after we cover all with the other pristine asphalt mixture. Now I would like to show you two short videos about the cell de-icing pavement demonstrator. As I mentioned before, the validation strategy followed was consistent on cover the pavement slab with ice and analyze the melting process. In the picture on the left, you can see that there are two different areas. The smaller area corresponds to the control area that is not heating during the validation test, and the large area corresponds to the area that is heated, that has dimensions around 1 meter by 2 meters. I'm going to show you two very short videos about. The first one is a time lapse or real photograph, where you can see the melting process, and you can see how the control area remains with the ice on the surface, and on the other part is melted. Okay. And the second short video is show the infrared images taken also during the process. The blue area the blue color corresponds to the ice. And again, you can see how the ice is melted. And here close to the screen you can see the control area. Okay. In this slide, I saw some results. In the picture, you can see the position of the thermocouples. We are using two types of thermocouples, one to monitor the temperature evolution and other to control the heating system. In the chart on the left, you can see the temperature evolution. It's easy to distinguish two areas. The first plateau corresponds to the part where the icing is being melted. When all the ice is melted, you can see here a sharp increase of the temperature because the heat is used by the system to heat the surface of the road. After 1 hour and 18 minutes, the ice was completely melted. The electrical current applied during the process was lower than 3 amperes, and the voltage applied was around 150 volts. The estimated electrical consumption was around 648 watt-hour per square meter and per centimeter of ice on the road. To conclude, I would like to highlight that this project is aligned with the European Commission white paper on transport that sets that by 2050 the European Union should have become a world leader in safety and security in all transport modes. And we think that the smart asphalt pavement developing MASTRO project has high potential as innovative technological solution to contribute to a smarter, safer, and more sustainable transport. The solution found is flexible because there is three functionalities developed, might be implemented separately or combined in convenient areas such as accident, black spots, airports, truck loading docks, parking areas, etc. With the aim of increasing users' safety, transport structures, lifespan, while reducing the maintenance costs. In particular, in the self-deicing pavement that I have shown to you, we think that represent an interesting alternative to other system pavement heating technologies, since combine the advantages of full conductive materials with a simplified electrode placement process that allow it to improve the energy consumption. Some open use issues are that the operating costs of the self-deicing functionality are still high. This make important to try to find synergy with other energy harvesting or clean energy technologies in order to improve the sustainability of this kind of development. To conclude, also, I would like to thank to the support and the hard work of the road group and the TICS group and the concrete group and the Obras Marítimas Structure groups of the Technology and Innovation Division of Acciona Construction. Also to our nano solution that produced the conductive bitumen with the graphite, with the conductive additives provided by Superior Graphite and Arkema. And also I would like to thank to Solidian that help us and support us to produce the carbon fiber grids that were used as electrodes. And as I mentioned before, this research was funded with the support from the European Union under the Horizon 2020 program. And that's all from my side. Thank you for listening to me. And if you have any question, I will be happy to answer them.
Yeah, I think there are no questions again. So yeah, I will give the word to Ignacio Del Far from Pinot Solutions, who will present the Master ICT platform. Ignacio, I don't know if you're talking, but we cannot hear you. At least me.
Sorry, now?
Yes, we get now.
Can you see the screen?
Yeah, we can, but it's not your presentation at the moment.
Okay. Now?
Yes.
Yes? Okay. Okay. Sorry for the inconvenience. I can repeat because I have just started. Let me introduce the company, a small introduction. We are an IT consultancy specialized in the development of cloud-based solutions, web services, always focused on business processes automation and business intelligence. We help companies to improve their services by implementing IT system in the cloud to manage data, to manage the daily operative of the companies, and well, to save money and be more optimal. We have clients for many sectors, from construction, manufacturing, logistics, and B2C, for example. And our role here in the MASTRO project is not directly related to the materials, but with the information that are produced in the demonstrators. Our aim is to collect all this data in a cloud platform and then monetize or analyze it in the right way. Well, I think the best way to know about the ICT platform, about the MASTRO ICT platform, is to answer in this presentation 6 simple questions that will allow us to have a relevant knowledge about what the MASTRO ICT platform is. First of all, what is the MASTRO ICT platform? Okay, what I have said, it is a cloud platform, a cloud-based platform. We can access it using a web browser, using not only a PC, but also a mobile, a tablet, well, any device that has an internet connection, we can use it to access the cloud platform. It collects the data from local systems. It integrates it in a common system. It manages this data. Sometimes data comes in different formats, in different files. Well, we have to standardize it to inject it in relational databases and collect it and classify it. Visualize data. This is, make dashboards with plots, with attractive designs to explore this data. And finally, analyze this data. Some tools to analyze, not only to visualize, but also analyze and take some data insights. Well, data from master demonstrators, not only that. I prefer to say from smart materials, master smart materials, because as I will explain later, our aim within this project is to design a system that is ready for the scale up, ready for the commercial stage, ready to be bigger, to deal with more data. So I prefer to say that this is focused on a platform that is ready for the commercial stage, for the future, for the next steps of master smart materials. The second question, why do we need an ICT platform? Is a natural question. Maybe, well, this project is focused on materials. Why do we need an ICT platform? Well, the data analysis and the data exploitation is a core part of any modern solution based on technology. For example, it helps in the process of decision making. I can take better or make better decisions in real time, just having a look at some dashboard, some indicators, some KPIs. So, well, decision making is a very complex process nowadays. So we need help from tools, from IT systems to back up, to support us on these kind of processes. For example, regarding predictive maintenance, this is a very beautiful consequence of managing a lot of data, that we can anticipate some issues. We will see it later, but we can anticipate, and we can make some decisions to avoid problems, just analyzing data in a proper way. Or another example, to be in a framework of continuous improvement. If I have all my data analyzed and all my KPIs up to date, well, I can make some decisions to improve my system in real time, to add features that are needed regarding the historical values of my system performance. Well, a lot of applications that are impossible to do without a proper treatment of data. Data is knowledge, of course, it's knowledge. If without the data, without data analysis, we can't have any conclusions. We can't learn about our system. We can't learn about our materials, and we can't go forward in the research of them. But also, it's money, as you will know now. The data it's a product that the providers send to third parties. For example, we know that Google are tracking data. Now Microsoft is tracking some data because we are using Microsoft Teams, and then this data is available for selling it to other third parties, other companies that monetize them. So data is knowledge, but also is money. So, well, let's make the most of data. Let's take this data, and later we can see what we can do with this. Another question: what is the challenge here? Well, Mastery is not an easy project. You can see it today that there are a lot of materials, a lot of developments, a lot of functionalities to be demonstrated. It's a big challenge to produce this material, and also it's a big challenge to deal with this data from the software point of view. So what we can do, first of all, keep calm and go step by step. Well, analyzing the requirements from a software point of view, from a software architecture point of view, the first of all is deal with different degrees of maturity. You know that in this project, the degrees of maturity have been very diverse, because some of the demonstrators were in a very early stage regarding the TRL classification, but others were in a more advanced stage. So, well, deal with different degrees of maturity when you are going to take data from the local environments are not so easy. It's not. It depends a lot what strategy you have to apply. Okay, this is the first challenge. The second challenge is integrate different sectors under the same approach, because it's not the same to work with automotive than work, for example, with transport infrastructure. A bridge is not like a car, for example. So it's very logical, but from a software point of view, it's a challenge also. And finally, there are a lot of demonstrators here. 10 systems are integrated in the ICT platform. So, well, this is such a challenge. Question number 4, how is the ICT platform implemented? Well, first of all, we have to ask end user for the technical requirements. This is, what do you expect from the ICT platform? Which features do you want us to implement in this system? Okay, well, after a lot of work, we can have that kind of scheme. This is a very aesthetical, this is not very technical, but I think it shows the complexity of designing a software architecture to deal with this kind of solutions. For example, here is the software architecture of AU4 of the demonstrator that is under responsibility of ALKE, electrical vehicles. Here, there is a dialogue between two edge computers, well, it's a Raspberry Pi, in case you know what it is. It's a very cheap PC, a very cheap personal computer that can be used in Internet of Things applications, okay? Here is an interchange of data. This system is have been constructed under the Internet of Things standards. Okay, it uses the Internet of Things principles to exchange data and to play with the communications. Okay, here we have the cloud deployed in this device, in the Raspberry Pi, and we manage the communication between the local environment. This is the demonstrator and the cloud. We transfer data using some data formats, JSON objects, text files. We implement the logic, the logic that is that underlies each module of the solutions. Each picture here is one web service or one service, one IT service that must be configured, programmed. It must be adapted to this architecture, okay? And once you are progressing here in this data flow, you join the cloud, okay? And you are in the application layer. We will see it later, where data is stored and data is shown to the end user. But this, the point that I want to show you is that the user sees is just a little part of this architecture. And this, we can call it the backend. This is the front end. This is the backend. And well, a lot of work has been done to have a very simple interface that the end user can manage, just clicking a couple of buttons. Okay, this is very easy. But our work here is to architect or to implement these different services. Okay. Well, after the designing, we must to implement, to test, to deploy the software. Is the common life cycle of an IT project. All the web services, the scripts, the connectors, the communications. This is a screenshot of our configuration of the Internet of Things, one of the services in this architecture. A lot of tests, but well, we did it. And I have mentioned it before. What do you see when you are using an application as, for example, Microsoft Teams, that is a web application? Well, it's a clean and intuitive user interface, a clean, user-friendly user experience, but underlying this, but in the you have all the complexity in the back end, but this should be very transparent for the end user. So an application that is very complex, that is very, you have to take into account a lot of configurations, a lot of buttons, is not attractive, is not commercial. You can't do that. So a lot of work have to be done in the backend to show, to offer the end user a simple, a clean front end, okay? And we have done this here also in the Mastro. Well, the best way to show the ICT platform is to have a quick view over it. So let me access the platform. As I have mentioned before, we can access using a simple web browser. I am accessing from Madrid, but if I were in Honolulu, okay, I could access also. The only condition is to have an internet connection. It's a simple condition, but not in all the places we have a smooth internet connection, but you just to have access to a web browser as, for example, Google, okay? Well, after login, because there is a layer of security that I don't want to show here because it's not very interesting, but you have your own credentials, your user, your password, you access here. We have the three modules, okay, of the solution separate. We are going to access, for example, here, the aeronautic module. Okay, you see here that, well, there are not many buttons. We have the self-functionalities here, self-queuing, self-sensing, because they are the main functionalities to be shown in the aeronautic module. And we have data here, data from experiments. For example, let me check. I think this is interesting, okay? I have two buttons, one to access experimental data, one to access the dashboard. Let's access the dashboard. Here, it's shown the metadata, okay? Metadata, it's a very core part of the ICT platform because metadata is very important to deal with data, to have the things that I have explained before, yes, to understand why data is like in one way or the other, okay? We need to know which this data where has the experiment has been made, the characteristics, the physical characteristics of the demonstrator. Okay, a lot of information that is not numerical values of sensors, for example, but very interesting information that must be taken into account and collected in the same way as data coming from sensor, from measurements. Okay, we see here a plot. Well, this is not very good because we see here, well, some plots make no sense. Well, this is very typical. When I am exploring data, some of the sensor make no sense. Here it's marking a very high temperature, more than the sun. So maybe this sensor is not connected. So, well, I can simply click in here. I am unmarking this sensor. And, well, the plot is adapted, sorry. And now we have adapted these thermocouples. In this case, we are measuring temperature. The plot is adapted automatically. If you are watching it through a mobile, it will be adapted to your screen. Okay, it's self-responsive. And well, I have here information of many sensors. In this case, the curing process. Well, it's a very relevant. The temperature of the part, but also the power, we can compare, we can extract here conclusions, where in this case, the relays that activate the system. You can see that if I hover the plot, I hover over the plot, I see the information, the specific information regarding this, this plot. If I click here, I can access to all the data available in a single time, okay? So it's very easy to manage, okay? And well, the plots are okay, are interesting, but I can access the experimental data, the SQL tables, and here I have all the data from all the sensors. I can apply filters, combining concatenating complex SQL queries to explore data. For example, I want to know data regarding a specific time or between two temperatures between two temperatures in a specific time. You can do many combination of conditions to explore data in a very deep way. For example, here, self-sensing, well, this is quite different. We access the dashboard of self-sensing. We don't see any data. We see images because the end user decided that, okay, here numerical values are not relevant. Here we have to show the relevant information that is just a thermal image of the part, okay? This is very important in the cloud world because you can't upload to the cloud everything because you will, first of all, because of the money you are paying for these services, and makes no sense to offer from an analysis point of view information that is not relevant. So this is a very good option to show here just images and no numerical values that can saturate the database and makes no sense, okay? Well, this is the one example. I have prepared here another. This is another module, in this case, the automotive module. And we have here some things different. For the AU module, we have here a plot of an experiment. We can apply filters. In this case, we are distinguishing between dates, okay? We can select the specific time slot to be shown. Here we can have the same features as they mentioned before, and this is very interesting. We can act over the system. Just clicking this button. In this case, the battery heating system is off. I don't want to activate it. I don't know in which state it is now, but the main thing here is that I can activate the system from any part in the world. If I am at home, for example, and I want to activate my textile sheet, I can activate from the mobile, okay? In case it's snow out there, I can preheat my seat or preheat some parts of the vehicle so they can unblock, for example, the door of the vehicle, okay? So this is very interesting because I can act over the system anywhere, okay? And well, I think the main features are shown. This is the databases. Okay, I think it's enough for a first introduction. Let me continue with the very last slides of the presentation. Well, there are two questions left. Question number 5, what are the main outputs of the ICT platform? Because we are in our research project. Well, what relevant outputs we have here? First of all, we have built a common toolbox with the help of the end users, a common toolbox of technologies to deal with the problems or the situations of the MASTRO project that is 3.5 years old. So it's a lot of time. So we are very proud to have this common toolbox of technologies in different layers of the solution, because the solution is like a cake. An IT solution is like a cake. You have different layers that all together makes the full functionality, okay? Hardware, for example, national instruments to monitorize the demonstrators, the Raspberry Pi, for example, to obtain data from sensors in a more compact way, because the Raspberry Pi is a very small device, okay? Regarding integration and communication, we have two different approaches. We have the IoT approach, Internet of Things, very good. For example, if we are monitoring a bridge in a remote location, we don't have a power supply, you can't use a switch to connect to the electrical wire. So, well, we can use an Internet of Things approach or a REST API approach. This is use HTTP methods to call the cloud and send information, okay? Python as a scripting language. We have done many lines of code using Python in this project, and Labi, of course, for systems that are at laboratory. The cloud platform, okay, well, we use Amazon Web Services to do some cloud computing, serverless approach that now is it's very on the top of the technology, serverless approach that you can dimension your system in function of which resources are you going to need in every moment. You don't have to pay for an oversized system. You just pay per use, okay? It's a very good thing of serverless systems, always hosted by Amazon Web Services. And regarding the cloud analytics, the application layer, well, we use Zoho as the provider of the platform, the ICT platform, and the business analytics tool. And also methods. We need a framework to operate because it's impossible to integrate different requirements in different moments in a project that is 3.5 years long without a methodology, a framework. We use Agile methodology, Scrum. We have developed this using increments of product increments, according to the nominative in the methodology, and they have been very useful for us because otherwise it will be very messy for us to deal with a project of this size, okay? Well, the main goals here, the definition, we have defined a set of best IT practices, okay? Together with the end users, we have a common framework to decide, okay, you can apply this approximation, you can apply this strategy to solve this technical problem regarding the IT systems, okay? We have detected, all the master team detected synergies between use cases. We have helped sectors of less maturity, less technology maturity to adopt solutions inspired in other sectors of more advanced sectors regarding the maturity of the technologies. We have designed it using very clear patterns. This is modularity and an easy scale up because for us it's very important that this system is ready to be applied at commercial stage. And don't be afraid of how many sensors, how many systems are going to be connected to the system. Well, it can work no matter how many systems are connected to the cloud. And the last one is this system is based on Industry 4.0 hottest technologies. This is Internet of Things, web services, serverless, edge computing. I think it's a long lasting solution because it uses the very last technologies available in the market. And just to conclude, the sixth question, what will an ICT platform 2.0 look like? Which is the next step? Well, I think the connection with artificial intelligence and machine learning tools. Why I think that? Because once you scale up this system, the system now is perfect to test the information on master demonstrators. But once you connect a lot of systems of the same nature, you can obtain a lot of data. When I mean a lot, is terabytes of data. You can connect this platform to artificial AI systems, to machine learning services, for example, in Azure or in Amazon Web Services, in Google, to extract high patterns, deep insights from data. It will be very, very useful, for example, to be applied for predictive maintenance. I can anticipate when a system can collapse, when a system can be damaged, and apply some rules to avoid it. Okay, this is very important because we are going to save a lot of money. Think about a very big infrastructure, for example, a bridge, for example. And regarding security, of course, predictive analysis is quite the same, and real-time optimization. This is very useful because my system is going to be optimized at real time, and I cannot do this without using machine learning tools or AI tools. It's impossible to optimize a system in real time without using these modern tools. So I think the next step is to collect a lot of data, to work, to operate with storing a lot of data, and then exploit it and analyze it and extract deep knowledge on it to be applied to serve this kind of tasks. And from my side I'm done. If you have any question, I will be pleased to show it to you.
Okay, thank you very much for this presentation, Ignacio. I don't see that there are any questions. So yeah, at this point we come to the end of the workshop. Of course, we have half an hour for open issues or discussions, but I'm not sure that there are any open questions left. If you have any questions, feel free to ask them, of course. So thank you all for your time and your interest in our workshop, and I wish you all the best with a lot of health and nice summer holidays.